Welcome everybody to Tuesday night. It's a Wednesday. I'm your host MCToon, and tonight we have one of my favorite people in the world, Professor Phil Bell, is going to be going over a little bit of the content of this book here. He has reviewed the book. It's a book by a flat earther named John Stunja, who also calls himself Quantum Eraser, as if he understands the topic, hilariously. Anyway, he's going to be covering, Professor Phil Bell is going to be covering a couple parts of, couple topics in particular. And here is Mr. Phil Bell. Professor Phil Bell, how you doing, sir? Your microphone.
Okay, there we go.
There.
Yes, I'm very well, thank you. I'm looking forward to this, and hopefully some participation from the audience. So when it comes down to that, let's explain to them what we're going to do. So this is a proper evaluation. So it's not meant to be mockery. Okay. I'm going to mark this like I would mark any paper, and it's got a rubric. We'll go through the evidence, and then we'll also present the evidence for why, I've chosen a certain mark for it. But I'm looking forward to you actually participating, and then go through the rubric with me, and then you can then score according to that rubric. Now, hopefully, some of you will be able to collate the information. So once you've collated, then what will happen is that we'll put them in a file, and maybe we'll do a box plot or something like that, so we can check for any outliers, and let's have a look at where most of the data sits, in which quartile most of the data is sitting. Okay, and that'll give us an idea. That'll be a fair evaluation for this particular work. Okay.
Very nice. I've got a pen. I hope it's the right color.
Okay.
For marking.
Yeah. So wait for the rubric, and then once we've got the rubric going, you'll be able to see what the criteria is. Okay.
All right.
So you've got to mark strictly according to the rubric. Okay. All right. Okay. So what I'm going to do now is I'm going to share. I'm going to share my screen.
Okay.
And so I guess I better open up the thing first. Okay, and we'll be going through one at a time. So let me just discuss that with you quickly. All right. So basically, firstly, we'll go through a brief history of gravity.
I don't see the share yet.
No, I'm not. Oh yeah, no, I haven't done it yet.
Okay.
So brief history of gravity. We'll then go on to the gravity, the rubric. So you'll get a chance to have a look at that. We'll then go through the claims that are made in that particular text, and I'll do my rebuttal of those claims. You can then score. We'll then go through the scores, and you make sure you put your scores in. I don't want to influence what you do, so I'm not going to tell you what I've scored until later. And then what we'll do is we'll have a look at that. A critical view in terms of this Stunja's work as a piece of science writing, and even as a literary work. So we're going to look at both, because usually I have to mark both literary work and science writing when I'm doing something like this. And then finally we'll have my final conclusion, and I'll be able to tell you what I really think. And hopefully some of you can clip that. Maybe we can turn that into a good clip that'll probably last about 5 minutes. Okay, or maybe less. All right. Okay, so let's start right from the beginning. So I'm going to, first of all, I'll bring up the brief history of gravity. Okay. Okay, and a slideshow from the beginning. Okay, so now I've got to do the sharing.
I do have, while you're getting that ready, I have my rubric ready in a cube form for later.
Yeah. Okay, that's good. All right. So all right, here we go. Hopefully you can see this. Okay?
Yes.
Okay, all right. So this is a brief history of gravity. Okay, so from falling objects to curved space-time. All right. Okay, now let's see. So I hit next. Okay. Takes a while to go over. All right, so here we go. All right, so 2,000 years of free-thinking gravity. All right, first of all, we started with Aristotle, so that was around 350 BC, and then onto Galileo and Kepler, Newton, who's of course the greatest scientific mind of all time, probably never to be repeated. And then we have Cavendish and Einstein after that. And of course, there's many others who came who've since validated the work that Einstein does, and of course, in doing so, validated the work that Newton did as well, because Newton and Einstein answered different questions about gravity. Okay, so neither is better than the other. Okay, let's move on. All right, so the what Aristotle thought that heavier objects fall faster. That was the intuitive thing, and I think probably most people who don't know anything about that, have never tried it, would probably think that too. It's a reasonable thing to think about. So everything seeks its natural place. Yes, that kind of is right anyway. All right, and earthly matter, the center of the earth and the heavens. Okay, it's the let me get that. It's okay. It's the fast. In other words, the faster it should fall, the heavier it is, the faster it should fall. That's what he thought at the time. And what was the experimental evidence? Well, it was just observation, because that's all he had. So, all right. He just simply reasoned from everyday observation rather than actually doing controlled tests. All right. So let's move on. So that was Aristotle. Oh, by the way, so the flat earthers are still at the Aristotle stage. Okay. All right. Even though they haven't answered, just like Aristotle didn't understand why in fact it does fall in the first place, let alone whether or not it should fall faster. All right. So here we have Johannes Kepler. So planets orbit in ellipses. He's famous for that, of course. All right. So that's Kepler's laws, are Kepler's seminal works. Okay, 3 laws of planetary motion. Orbits are ellipses. That's we can measure them. So whatever the people like Stunja say, we measure them. So it's indisputable that they do, that the planets go around the sun, and they go around in their orbit is elliptical. So if they've got a sun that's going around a pizza, the top of a pizza, that doesn't remove the fact that the planets are going around the sun while that sun is going around the Earth, like it's going around the top of a pizza. So the planets, it's incredible how that happens, because I mean it takes years for some of the planets to go around the sun just even once, and yet they manage to go around the sun in less than 24 hours. So I don't think Stunja thought about that. I think that completely went right over his head. Okay. The next thing is, whoops, I went a bit too far with that. All right. So built on Tycho Brahe's data. So Tycho Brahe did a lot of the observational work with that, and you'll see. And of course, the Kepler's great thing is where we saw that the square of the period is proportional to the area, the cube of the area that's the range, the cube of the range. Okay, so t squared over r cubed is Johannes' seminal work. All right, so the law of ellipses, okay, is what he called it. All right, the 3 laws of planetary motion. So every planet moves along an ellipse, okay, with the sun at one of the 2 foci. Okay, so orbits are not perfect circles. Actually, pretty close though. I mean, if we're only talking about in 150 million kilometers, just a few million kilometers difference. It's almost a circle. It's actually not far from being an actual circle. The law of equal areas, all right, a line from the sun to a planet sweeps equal areas in equal times, so a planet speeds up as it nears the sun. Okay, so it goes a little bit faster as it goes this way around here. Okay, that's one of the laws of planetary motion. Okay, and ellipses. Okay, and then the harmonic law, so orbital period squared, is proportional to the orbital size in cubed. So t cubed over t squared over a cubed, or t squared over r cubed is generally what you'll see in physics books, that we r cubed being the range. Okay, so Galileo came along, and he actually did the first part of the work that finally led to what we understand about gravity, and that is having an inclined plane and then testing to see if indeed things with different mass fell at different rates, and quickly found out that that's not true. In fact, if you account for the inclined plane accounted for friction, which is similar to both, and Galileo was able to show that things fell at the same rate regardless of their mass. Okay, all right. So all bodies do fall at the same rate. Now that from the perspective of understanding gravity is extremely important, because that means that there's something about this falling that's important, that's unique, that it's you'd expect things to that are heavier to fall faster, and yet they don't. Okay, there is something there that makes that something that sounds intuitively impossible possible. Okay, so what that does lead to, thinking about that, and we'll talk about Newton shortly, what that does lead to is to think about the this as being a field. In other words, it's common to everything. So the way this field behaves, the way things behave inside this field is common to everything. Okay, so inclined planes and the Leaning Tower of Pisa, as you know, right, by rolling balls down the inclined plane. Okay, that's in the early 1600s. Okay, Galileo, diluted gravity enough to time it. So that was the big thing. And of course, millions and millions of students all over the world doing physics in high school use the ticker tape and actually do this experiment and show the acceleration. They actually measure the fact that falling things accelerate. I recall doing that probably in maybe the first year of high school, something like that.
I remember that too. And now you can use your phone.
You can use your phone.
You don't need an inclined plane.
Yeah, exactly. You could record the whole thing. In those days, it was a big deal to get a Super 8 movie camera and set that all up so that we did that. Okay, we did that at university, but in high school that was a big deal to set that up. So we didn't have the privilege of doing that, and now you can just stand there with your phone and record the whole thing and use your phone to measure it. That's fantastic. Okay, just as a side thing with the phone, I recall saying something. What's the future? With the future of technology, and I said to the teacher, wouldn't it be amazing if you could ring somebody up and see their face as they're talking to you? Wouldn't that be amazing?
That'd be amazing.
Of course, we all concluded that would be totally impossible.
Yeah.
So, and yet here we are. We actually do that, and look at us talking like this now.
Yeah.
It's just unbelievable. Okay, so experiment and evidence. So inclined planes and the Leaning Tower. So by rolling balls down the track, we worked out, okay, the famous Leaning Tower thing, that's what became famous. dropping two things and then realizing that they fall at the same time. So we knew that there's something about it. It's something different than just something falling. It accelerates at the same time, okay, at the same rate. Okay, then here we go. So what did he establish? He slowed down the gravity down, didn't physically slow the gravity. The experiment, he was able to measure the experiment, found that the acceleration was uniform acceleration. Okay, distance grew with the square of the time. So you can see that that's like the ticker tape measuring that. Okay, all bodies fall alike, and far beyond falling. Okay, like pendulum timing, parabolic projectile paths, and telescopic proof of a sun-centered system. So that was the other benefit that came from that, and saying, well, you know what? That's this fact that things accelerate as they fall together. There is a relationship between that and what we observe in the heavens. Okay, all right. So so then Isaac Newton, greatest scientist of all time. Okay, Isaac Newton, the great idea that universal gravitation, every mass attracts other mass. Now, we'll talk about this a bit later, and people like Stuya, in fact, all the flat earthers say, which gravity? Is it Newton or Einstein? Well, it's all the same. What we see, what we experience from Newton, and this is what Newton quantified, and that is the things do attract each other, and there's evidence for that, of course. Okay, and Newton wrote about that. Newton never said that didn't happen, which is the lie that we get from flat Earth. The big lie is Newton came out and disowned gravity altogether and said you'd have to be some sort of fool to believe it, and then Newton said nothing of the kind. So what Newton did say in that was that I don't know why these two things should attract each other. I don't know why they would do that. That's all he said. And so he was saying you'd have to be a fool to believe in magic. There's obviously something about that that needs to be understood, and Newton didn't understand that at the time. So he prompted. So he wrote about it, and of course that was his seminal work. Apart from all the other hundreds of things that Newton did, invent calculus. Who needs that? And if you say that to anybody who's ever done any calculus at all, your mind just blows, and you think, well, wow, a person invented that. And guess what? He was like 24 or 26 years old when he did that. Okay, so it's just so incredible, that this is what we have now. We can't do engineering without calculus. So this is one of the things that he did. Newton looked at light, all sorts of different things. He had a smorgasbord of things to look at, a smorgasbord of mysteries, if you like. And Newton was able to, he had the brains to look at all of them. Right. But this one here, universal gravitation, is what he's remembered for. Okay. And of course, for the people who do know better, he's also remembered for calculus. All right. So let's move on. So one equation that governs the cosmos. So the force is equal to G m1 m2 over r squared. So one mass times the product of two masses divided by the square of the distance between them. And you notice that big G, Newton didn't come up with that. Okay, that came later, and we'll talk about that in a bit. And that came later because what Newton told us, Newton didn't say that force was equal to the m1 m2 over r squared. He said that it was proportional to that. That's what Newton said. Now the thing about an equation and an expression of proportionality. So an expression of proportionality would say that force is proportional to the two masses over r squared. In order to make this an equation, to make an equality, now we have to introduce a constant of proportionality. So the constant of proportionality, that's what big G is. And that can only be done by experiment. So other people have to come later, which we'll talk about, come later and then work out what this constant of proportionality is. So anytime you see you see an expression that talks about proportionality, there's going to be a constant of proportionality that deals with this. For instance, Hooke's law, okay, F equals Kx. K is the constant of proportionality that describes the spring constant, for instance. Okay, all right. So we look at that FG. I think everybody here knows what those things are. So force, the gravitational constant, the constant of proportionality, the masses, and then the distance between them. So when we talk about the distance between them, by the way, we're not talking about the surface of one to the surface of the other. We're talking about the center of mass of one to the center of mass of the other. So that's
flat earthers get that wrong at times too.
Yeah.
They think that the surface of the Earth should be maximum gravity.
Yeah, exactly. Okay. All right. And so here's our man, Henry Cavendish. Everybody talks about Cavendish, and everybody points to this work as the if you like, the strong evidence about gravity. But actually, by the time we got to Cavendish got to do this, it was accepted science. The idea of gravity was accepted science, and so what Henry Cavendish wanted to do with this was find the density of the Earth. In other words, weigh the Earth. Let's see what it is. So Newton's law had a missing number, the strength itself. That's the gravitational constant. Okay, and Cavendish set out to measure the faint pull. Okay, right between two lead spheres in a laboratory. So if you think about just a minute. So if you think about gravity, and you accept that mass attracts mass, then it doesn't mean that it's just falling down. Okay, if that actually is the case, then the hypothesis would be that if we think that mass attracts mass, then mass attracts mass no matter what, whatever direction. So the hypothesis here is saying, well, if gravity is true, in other words, mass does attract mass, then two objects horizontally opposed will attract each other because the most of the gravitational pull is by the Earth, but they're equal for both of them, or almost equal for both of them. In other words, the difference between is marginal. So now we're actually observing gravitational pull, horizontal pull. Okay, so a lateral pull. So that strengthens the idea of gravity. So if we just drop things and then people just say, "Ho hum, yes, well that was happening already," and but this actually shows that that laterally they attract each other, and that was key to this experiment of Henry Cavendish. Heard many people, including Stunia, say, "Well, that's not an experiment." Well, just in a nutshell, because this show is not about whether or not what is science, but it is an experiment because we make a prediction, we observe something, we make a prediction about why that thing is happening. We then test that prediction. Okay, in many ways, test it as many ways as you can. So take out any variables that are confounding. So control those variables, and then have a look and see if in fact your prediction is true. So you have a hypothesis, you've made a prediction. You then design an experiment that actually answers that question. Okay, so Henry Cavendish, the torsion balance experiment in 1797 to 98, so it took a year. Yeah, all right, using a delicate torsion balance. Okay, that was designed by John Michell. He detected the tiny twist caused by the two spheres attracting them, and then as a result of that, was able to work out what that gravitational constant is. So you can see what the force is, because the force is, he can work out what the force is based on the amount of twist, knows the two masses that he put together, knows the distance between them. So therefore, rearrange the formula so that the gravitational constant becomes the subject of that expression, and then solve for that. And that's how we got the gravitational, and that's how it's still done today. Okay, except to far, far, far better accuracy. Okay. All right. So weighing the Earth with a twist of wire. So the density was of the Earth is 5.4 times the density of water. Okay, and in just to 1 sig fig, 6 by 10 to the 24 kilograms. So I think most of the textbooks will be saying we'll give it 2 sig figs, and I'll talk about 5.8. 6 is close enough. 5.86. Okay, then G has worked out only with three significant figures, 6.67 by 10 to the minus 11. Okay, I think we're up to about 15 or something like that. Okay, and of what's accepted now, because of all of the modern equipment that we've got and the ability to do this with much, much better precision, found that was just within 1% of the figure that we've got now. So it was pretty good. I mean, you've got to hand it to Cavendish in the think about the equipment that was available then, and the equipment that's available now. You know, he didn't have lasers and stuff like that we've got now, and still been able to get within 1%. Pretty incredible. By the way, Henry Cavendish did lots of things as well. Okay, so he was involved in chemistry as well. So let's not forget all the other things that Henry Cavendish did. If you're interested in history, especially science history, read about Henry Cavendish, and you'll realize what an important scientist he was too for us.
He also, fun fact, he also invented the banana.
There you go. Okay. I got no comment on that. Okay, here we go. Okay, so gravity is so now here comes the Einstein. So let's get back to that idea about about the difference between Einstein, what he said, and what Newton said. So Newton, as you know, and he spelled it out very, very clearly, he didn't understand why it's happening. He measured it. He worked out that all of the things that we see around us, in other words, all the motion of the planets, the motion of the stars, where things are, why they're there, completely managed to measure those things, and then come up with the and realize what that proportionality is, force proportional to m1 m2 r squared. So that was based on empirical evidence. Okay, so what Newton did say is, this is what happens. Okay, and this is what happens, and this is how we can predict what happens, because that's the most important thing. What's the use of it if we can't predict? And we can say, well, this is what's going to happen if we have these conditions, and it works all the time. So as far as we're concerned, Newton's work is what we rely on. We don't go to, engineers don't go around, I've got to work out the strength of that beam. Let's include all of the 10 tensors, Einstein's 10 tensors, to see if we can come up what the strength of that beam is. No, they don't. It's just going to go F equals mg.
Well, if you need 12 sig fig.
Yes, if you did need that, and of course your saw for cutting that beam couldn't get that kind of precision. So that's totally ridiculous. I doubt you probably couldn't get within a millimeter cutting an F-17 beam, for instance. Okay, all right. So Einstein, on the other hand, his work was, well, sure, I agree with Newton. It happens, and I agree with Newton. It happens like this, and I agree with the data. I agree with the conclusions. But what was missing here is why it happens. So this is what Einstein and Einstein, looking at that, um, could only really come up with one conclusion, and that is it had to be a geometric problem. Okay, it couldn't. There isn't a way, and Newton spelled that out in his in when he denounced people as stupid if they thought that it was magic. Um, he must have thought about that, although he didn't follow it up. He must have thought about that it had to be something like that. It had to be geometric. There had to be a geometric reason for this to happen. So Einstein actually put that together, and so Einstein worked out that, yes, this was all about geometry. Okay, so gravity is not a force. In fact, nobody ever says that it is. So what the gravitational field does with an object in the gravitational field is create a force, create the conditions for a force. So if something's going to accelerate, then we have the conditions for a force, right? So it's not so the idea here is that gravity is not a force pulling across empty space. Okay, mass and energy bend the fabric of space-time, and objects simply follow the straightforward path through that curvature. So, so one of the things that we get from flat earthers and Sturnia in particular is he'll say, well, how can you bend space? How can you bend a concept? This is one of the things they have. Well, I would say to that, your powers of imagination, of deduction, of thinking in general are very, very weak. That would be my conclusion for someone who says something like that. Okay, so we think about space, we think about time. Well, if you hold your palms together like this, and then spread them like that, you agree that we have some space.
Yes.
You didn't do that without time.
Yeah.
Okay? There's no way for that to happen without time. They are intrinsically linked. You cannot separate those two. You can't make space without involving time. So it's fair enough to say that these things that these things are linked in that way. And if we think about space as being, and time as being something we could say, well, what if this was we could we could cut that up into blocks, into measurable blocks, just like we can get a ruler and turn it into millimeters. We're looking at that, and there's nothing there, and there's no mass there. Then we could say that would be, those blocks would be uniform in 3 dimensions at least. Okay. All right, so in the 3 dimensions of space, they would be uniform. And then we also have time. So time is a continuum, and we can measure time by breaking it up into small chunks. So we call it seconds. All right. So if we got space and time, and we think about if something's in a position in space, and it's going to move to another position, then effectively is going to have time. And so what happens is when you introduce something to this space-time grid, if you like, we now change it. So it's no longer that nice uniform thing that it was. It's now changed in different ways. So in other words, it's changed in proportional to the thing that's there. So, for instance, the Earth creating a gravitational field. So in other words, that bending of the space-time, that well that it creates is the gravitational field. Okay, and that gravitational field is proportional to the amount of mass that is there, wherever it is. So not all parts of the Earth have the same have the same mass. So some parts of the Earth are heavier than other parts, and there is a difference. So it's not always 9.81. That's just like an average. Okay, and the wonderful thing about that, it not being not all 9.81, is that we can use that piece of information. That's a useful piece of information that tells us if about the mass of something that's causing that difference in the gravitational field strength. And by the way, one of the flat earthers like to say, well, that little g. I think that if you put it in a nutshell, they would say that gravity causes gravity. That's what we would say. Gravity causes gravity. Well, they've got that totally wrong. So the fact that mass is in a gravitational field causes the change to that to space-time that changes the geometry, and that in effect creates a gravitational field. So anything that's in that then falls into that gravitational field that's created because of that is then affected by that. So Earth creates a gravitational field. You're an object. You want to jump off a building? Fine. Well, you're the object that's there, and you are affected by the gravitational field strength that's created by that. Now, one of the things that we all like to know is we'd like to know, well, how much is it? How the hell do we figure out what this gravitational field strength is? Well, the great thing about that is what Galileo discovered, that mass is irrelevant, that acceleration will be the same for everything. Bingo! There's our measurement. There's our device by which we can measure the gravitational field strength. So that's what we use. So vicariously measuring the gravitational field strength, we use acceleration. Does that work? You bet it does.
Yep.
People who are using gravimeters to discover minerals underground prove it, that it works. Spacecraft, satellites, you name it. All of these things show us that in fact it's true. So thank you, Albert Einstein, Professor Einstein. Thank you very much. Okay, so predictions beyond Newton. Of course, Einstein very famously said that when asked whether or not that he had dumped Newton, and of course he said no. Einstein was much smarter than to denigrate the smartest person who had ever lived. Okay, so he said no, and in fact uses the gravitational constants used in his equations. Okay, so general relativity, which is what this became known, exactly explained the slow twist of Mercury's orbit. That was one of the things, its evidence, and Newton couldn't do that. So Newton couldn't find that didn't have the precision to do that. Okay, that was the issue with Newton's gravitational proportionality. He had that, but he didn't have the precision to do that. But Einstein's, because Einstein knew why it was happening, and Einstein knew, well, this is the product of geometry. He's able to apply principles of geometry to get down to this extremely fine detail and be able to make predictions that are much finer than Newton could ever hope to do. But like I said before, We don't need that kind of prediction. So if you're building a building that's even a huge building that's maybe 100 meters wide, no one's going to care if it's out a millimeter. Okay, so we're talking about that sort of scale, and even less. All right, so why gravity really isn't really a force, as I've said before, that's got to do with the equivalence principle. Okay, so if we look at that, that's mentioned a lot. I think Whitsitt mentions that a lot. Standing on the Earth feels exactly like accelerating in a rocket. Okay, gravity and acceleration are one and the same. All right, so they're one and the same. In other words, we can measure the gravitational field strength using acceleration. Okay. So mass bends space-time, matter and energy curve the fabric of space-time, and objects just follow that the straightest available path. And then the field equation. Well, I won't go through that, but if you're interested in having a look at the Einstein's field equation, have a look at it, and probably watch a video on it, on how it's derived. That will take a long time, and for most people, it'll probably be a bit boring, unless you were really keen on maths. Okay, so a century of confirming Einstein, the bending of the starlight. That was probably the most mentioned of the evidences that was produced. So prediction. Einstein predicted that would happen. That light would bend as a result of the gravitational gravitational field of the sun, which it did. Okay, so that was predicted in 1959, which I want to talk to you about that, and that was gravitational redshift. I'd like to talk to you because I haven't heard that mentioned much in this discourse on flat Earth versus.
I've brought it up a couple times, specifically with Alan space audits, and he had a load of nuh-uh for it.
Yeah, that unsurprising, but yeah, I think it's worth. I'll have a little chat about it. That's the Pound-Repko experiment, which in 1959, and that basically showed light loses energy climbing out of Earth's gravity. So as it leaves Earth's gravity, it loses energy, and therefore it confirms that gravity does slow down time. And we know it does because there's two things that affect the time on satellites. There's two things, and that is the special relativity, so time dilation, and there's also gravitational redshift. Now, the gravitational effect is actually bigger than the time dilation effect. So in fact, and I've got some numbers on that. It's about quite a small percentage compared to the actual gravitational change because of general relativity. So that's actually bigger. So I'll if we get to a chance, I'll get some figures and we can have a look at that and see how, in fact, adjustments to the clock before the satellites actually launched, that's made here on Earth. So it's very carefully worked out. This is how far we want the satellite to be. This is what the velocity of the satellite's going to be. This is what the gravitational field strength is going to be at that particular location. And therefore, this is the difference in the time in the clock that we'll get as a result of both the gravitational field and the time dilation. Okay, so that's all worked out prior to even launching that satellite. So once the satellite is in orbit, then after that, once they're continuously making corrections to the time, that's done here on Earth, and that information is then sent to the satellites. The satellites then use that correction, and those corrections are then broadcast to the wider community that then use that information to get the distance more accurate. Okay, because obviously if the time is out, actually it's a very, very small change in time makes a huge difference in the distance. Okay, so the next thing after that, very soon, not long ago, actually, gravitational waves, the discovery of gravitational waves, and then and again, Einstein predicted that. And then the first black hole image, which was in 2019, also predicted by Einstein. So this is just four pieces of evidence. There's much, much more than that that confirms Einstein's that it is geometry and makes sense that it's geometry. Okay. All right, that was the end of that particular run. That's our brief history of gravity. So I'll just screen sharing has stopped. Good, thank you for doing that. Okay. All right. Okay, so go over that a bit at a time if you want to look at it more closely, and then you can use that as a springboard to actually do some of your own research and read it. There's so much there to read and learn, and it's really exciting stuff. Okay,
there is a rich background that certainly the people that seek to dismiss it blindly are generally quite unaware of. So thanks.
Absolutely.
Can we have a moment here to go over a little bit of the? I got some super chats and stuff from the audience.
Please go for it.
We've got Karen Monson is a new member at Newton. Thank you so much for being a member. Tim Davidson says Newton invented calculus during a pandemic. Do you know how bored you'd have to be to invent calculus?
Yeah, yeah. Imagine that.
Also, I was asking in the chat, is it possible to create a Fig Newton using bananas? Because then you'd have a Cavendish Newton.
There you go.
Tim,
go ahead.
Tim Davidson says, hello, my baby. Hello, my honey. Hello, darkness, my old friend. There you go. You were thinking it was going to be a Bugs Bunny dancing frog. Max for 30 Uruguayan pesos, Max with all 4 stars, says, you are all saying it wrong. It's Juan Estuña.
Okay.
That's his name for quantum eraser. And Basil Problem with his, just so you know, Professor, Basil Problem is also the same guy as 1 over n squared, and he's a bit of a troll. And I have a rule for him. It's my extortion rule. Every one of his super chats needs to be a higher level than prior. So his $2 super chat he overpays and it pays $5 for. It says Basil is back, baby, and he's coding in Java 8. And I'm switching to just coding in Python 1.5 because that's the book that's got the rats on it, and that's the only one I'm using. Anyway, Basil Problem's next super chat has to be 5 or more. There you go. All right.
Okay, so I just want to briefly explain to the people who aren't mathematically inclined or don't know this, and you know, you can be forgiven for not knowing this. It's fine, and that is why we actually have calculus. And what's it all about? Well, there's 2 main things that you would study probably in late high school and even at university level, and that is, first of all, looking at the rate of change of something. Okay, so generally speaking, if you accelerate uniformly, for instance, in your car, and you were able to plot that with distance over time, you'd with the speed over time, you'd be able to see that you'd get a straight line, so it'll be linear. Okay, all right. So that would happen but in reality, you couldn't make it linear because acceleration in your car depends on how much energy you give it, and that would be very difficult to do that uniformly. So you need a machine to do that uniformly. So what happens is that it doesn't end up being a straight line; it ends up being a curve. So therefore, what we need to do now is to say, well, at a given time, could we work out what the rate of change is at a given time? Right, and this is the purpose of derivatives. This is the purpose that we have this part of calculus. What is the acceleration, for instance, in a velocity time? So we're plotting speed or velocity versus time. So the rate of change, the rate that is, in other words, the way that curves, or if it's linear, that rate of change is actually a measure of the acceleration. Now, the next thing is they will say, well, okay, well, for displacement, which is, sort of the distance, then we'll say, well, how would we get that? So if we had that, we'd want to get the area that's underneath that curve. Okay, and we call that integration. Okay.
Yep.
All right. So or antiderivative. So we're finding the area under that curve. Now, if you think about it, how could you find the area under the curve? Well, you could divide that into very, very small blocks and then count them. Okay, or into very small rhombuses, and you could work out the area that way. Okay, so you've got.
Wait, you said rhombus. You've left the flat earthers behind now.
Oh, okay, all right. So if you're not sure what a rhombus is, then have a look at it up. Okay,
that's right. Left to your own. Yeah, you Google that yourself, laddies.
That's right. So have a look at what a rhombus is, and you'll get the meaning. You'll get what I mean by that. So you can slice that up into very, very, very small slices, and then count them. Okay. Now, you could then count them in such small sizes that there would be an infinite amount of them. Okay, that would make your calculation of the area under the curve extremely precise. Right. Now, Newton had to do this. Newton understood that he had to actually achieve this in order to get where he did with his calculations. So he had to know, how could I get there? How could I work out what the area under this curve is? By estimating, for instance, if there was an infinite amount of rhombuses that I could add up and therefore get the whole area. And this is this is how Newton came up with integration. Okay, and integration tells us then gives us a precise number. Between 2 points on a curve, so it's not the whole curve. You still got to break the curve up in different ways, because you have to have you have to have the recipe for the curve, if you like, if you want to call it that. It's the equation. For instance, if it's a parabola, the recipe, we could say that every value for y is equal to the square of x, for instance. Okay, so that would create a parabolic curve, and then along anywhere on that parabolic curve, you could then work out what the rate of change is. Okay, and then and between 2 points on that parabola, you could work out what the area under that curve is, which would be, which is of course important, because the area under that same curve, velocity time, is going to give us a displacement. Okay. I encourage you to get if you haven't done any calculus before, get a beginner's book on it. Obviously, your algebra has got to be probably a bit better than average, but you could get there by learning, and then you'll see it's a pretty exciting field of mathematics to get into. And then and then it goes on to double derivatives and triple derivatives, and you can really, really go to town with it. Okay.
Yeah. Double derivatives for instead of an area, a volume, and triple derivatives for a volume changing over time.
Yeah, exactly.
Things like that.
And of course, we have computers that do that now, and they do that in such a way that they even actually show us diagrammatically how these changes are happening. It's just amazing. So computer, what's happened. When I first started university, there were no calculators. Okay, calculator wasn't a thing. Accountants had them, and I think the best thing an accountant could do was find the square root of something. Okay, that was about as sophisticated as they got. for we had a
Slide rules.
yes, a slide rule like that, exactly, and a little thin book. Mine was green, called four-figure log tables. Okay,
Oh
which
yeah, all of the nautical almanacs and nautical ephemerides have them in the as like a huge portion of the book.
Yes, yeah, no, awesome. Because now I got a calculator and all that. I go through that and I actually point it out to students, and then we can actually see the patterns in it. And because that was the useful thing about having four-figure log tables that you can't get on a calculator.
Yeah.
You can't actually see the patterns that are there. You can't actually see the relationship between, let's say, we're looking at right-hand triangles, and see how the change in the size of hypotenuse, if the change in one side affects the other. So the change in one angle has an effect on the other, and the relationship between them. So for instance, we see that the sine of, let's say, 30 is 0.5. So that part, if you're looking at a unit circle, again, that's 0.5, and the cos of 60 degrees, which is the complementary angle to that. Okay,
It's
the cos
also
of 60
0.5.
degrees is also 0.5.
Yeah.
Okay, so you can
Cos,
see the
cos for
relationship between them.
people at home, cosine. Cos is cosine.
Yeah, yes, that's right. And the other side is root 3 on 2, and that's 0.866. And again, that changes. So the sine of 60 degrees is 0.866. The sine of 30 is 0.5. The cosine of 60 degrees is 0.5, and of 30 degrees 0.866. Perfect relationship between them. Okay, all right. So enough mathematics. Let's carry on with the next one. Actually, there can never be enough mathematics when we're talking about physics. Okay, so here we go. So now we're going to have a look at the rubric, and this is what I'd like you to go through carefully, because this is what we're going to measure. So make a little note for yourself. Okay, make a little note for yourself, and I think I might shut this one down so I don't get confused. Okay, and let's do show and then from the beginning. Okay, so here we've got a critical assessment. Okay, so rubric for evaluating scientific and literary writing maturity.
You haven't shared it yet.
Oh, I haven't shared it. Okay,
Yep.
good. I better do that, hadn't I? Yes. Okay, just a minute. Better do that. Okay. And here we are. I need to share. I think that's the one there. All right. Okay, is that good? You can see that?
Yes.
Okay, so this is the rubric. So rubric is like a I wouldn't call it a recipe. I'd say instructions for how to actually because you want things to be fair. You want to measure things the same way for each thing you look at. So when we're doing an assessment, for instance, it could be asking somebody to write a paper, or it could be an assignment of some sort. Then we'll say, well, you get so many marks for getting this far, so many marks for getting that far, and so on. So then we're able to be fair about how we mark it. Otherwise, before people used rubrics, it was pretty subjective, and maybe if the professor liked you a lot or the lecturer liked you a lot, then you got a higher mark, because it was pretty subjective. But now it's not subjective at all. So because we use things like rubrics. So here, chapter 3, the gravity of the situation. I won't comment on that title. Welcome to Flat Earth by Stunya and Macon 2026, and that's what we're going to deal with. Okay, so there's 6 criterion that we're going to be looking at. 6 criteria, and then each is a criterion. Okay, so the first one is the use of scientific terminology. So we'll give a mark on that, and you can see here the marks are very low. They get 0, If it's low, they get 1. If it's medium, they get 3. And if it's high, they get 5. So that's how the marks are basically distributed for each of those criteria. So the second one, structure and logical progression, how whether we think that deserves a very low. In other words, it doesn't exist at all. Maybe there's some of it there, the little flame. So we might give it low. If it's okay, it's all right, maybe it's okay. And if it's really high and say, yeah, that really hits the mark, then it'll get 5. Okay, the use of evidence. Needless to say, I bet everybody knows where that's going to go. Tone and objectivity. That's important. Okay, so in other words, what's the tone of this and the objectivity of the information that's being given to us? So we're going to mark that either between very low and high. Okay, then we look at argumentation quality. So the quality of the argument. This is not the argument. This isn't the whether or not it's right or wrong. So a lot of this is not based on whether it's right or wrong. We will discuss that, whether things are right or wrong, but and you can develop that from the history that we went through already. But this is really about whether the argument stacks up at all as an argument. Okay. And importantly, because this is a published book, we need to look at its literary maturity. Okay, so in other words, as a book that's purporting to be science writing, if you like, although it does say in the beginning that it's a work of fiction, that's worth noting. But it says we do need to discuss the maturity of it. In other words, who's it aimed at? Now, frankly, it's aimed pretty well at those people who think that the Earth is flat. I think it would be fair enough to say that. Okay, so I would give it 10 out of 10 for its audience. Okay, it nailed it. That's who it's aimed at, and actually as a novel that's aimed at that particular audience, it is. But that's not what it's being passed off as. It's being passed off as science writing, and that's how we're going to mark it. We're going to mark it off that it's passed off as a work of literary work, and a literary work that's involved in science. Okay, so if we were to mark this as a work that's involved in comedy, if you like, or something like that, then we might mark it differently. But we're not. We're marking it as a work of science and a work of literature. Yeah. Okay. All right. So criterion 1, the use of I'm just going to move us out of the way. Use of scientific terminology. So if this happens, now pay attention to this well, and that is high. Give it a high if you think the terms are used accurately, consistently, and with clear definitions. In other words, it's unambiguous. Okay, so in that case, if it were all of those things, when we look at it, we'll be looking at specific passages in quotes, and then you decide whether you think that's high, or if it's medium, the terms are mostly accurate, but occasionally loose. All right, then you give it a 3. Okay, and if you thought it was the terms are used rhetorically or incorrectly, so flat out just wrong, or it's just used as rhetoric. In other words, there's nothing behind it; it's hollow. All right, and then if you very low, if you thought the terminology is misused or it's undefined at all, or distorted, okay, or non-existent, okay, and then we say, well, that's then you give that very low. In which case, give it a 0. Okay, all right, okay. For criterion 2. The structure and logical progression, give it a high if the argument flows logically with clear connections between the ideas. All right, so it's not some sort of gish gallop and broken up into bits, and there's no connection between those. So medium, mostly coherent. In other words, it follows each other, but includes minor digressions or jumps. So the occasional mistake where you've got some digressions. And then low, if you think there's frequent digressions, it's unclear progression, there's no connection between them, and circular reasoning is part of that. Okay, and then very low if the argument just lacks any kind of structure or coherence at all. So let's just blurt out some words, and then hopefully they fall in some sort of order for you. In which case you'd give it a 0 for that. Okay, for number 3, the use of evidence. So again, pay attention to that. Evidence is integrated critically and supports the claims directly, is unambiguously, right? In that case, we're going to give it a high. We'll give it a medium if the evidence is present. We notice that there's some evidence there, but it's not always analyzed. So in other words, it's just blurted out. Low if the evidence is quoted without any explanation or used superficially. In other words, just put in a site. Well, somebody said this. George Musa said this, and so what? So what if George Musa says anything, and so what if Neil deGrasse?
Yeah, that's not evidence.
That's not evidence, exactly. All right, that's just somebody saying something. Okay, and then finally, evidence is misrepresented or completely absent. So you just say stuff, just make a claim, and don't provide any evidence for your claim whatsoever. All right. I frequently hear that saying, well, we don't have the burden of proof. Well, you do. You said the earth is flat. So, you said all sorts of things for which there are consequences for saying that. And each of those consequences, you vicariously are saying that. So if you're saying that the earth is a pizza and the sun is going over around the top of it, there's a lot of things that you're saying within that, okay, which we can then separate out. Okay, where is it at such and such a time? How does it set? There's a whole bunch of stuff that we can then questions we can then ask about that particular claim that you've made, and all of those things necessarily have to be answered. Okay, so this business about, well, we're saying it's not a globe, but we don't know what it is. Again, that's toys. All right, that's not scientific writing. All right, you need to offer something that tells us why you think something is such that, and where it's wrong. Okay, in that. So don't just say, well, I don't think it's a globe because it doesn't do this or doesn't do that. You've got to say, well, why? Where is it wrong? Where does it go wrong? What words are wrong?
And what
phrase is wrong?
If you're testing the globe, you have to be correct about how you construct your tests of the globe, which is generally a major failing of what the flat earthers do.
Well, they would, for instance, their laser tests. That's the thing that they hang on the most. Laser tests, and then, but for this one, we're just going to ignore the fact that refraction is a thing, and we're also going to ignore the fact that divergence. Okay, I've got to answer this. Okay, so I'm going to. So if you can mute me, please.
Sure. All right. While he's off on the phone there, I will, very important phone call. Oh, he told him to call back. You are all more important than whoever called him.
All right. Okay, so if you can unmute me.
Yep, you're back.
All right. So I forgot to give you this warning. That was just somebody from India trying to sell me something, so I've dismissed them. Okay.
Oh. I know him. He called me too.
Yeah. Yeah. So yes, it happens all day. But no, I'm actually waiting for a call from my doctor. So if you can, Michael, as soon as I say, look, I've got a call coming, please mute me.
Sure.
Okay. All right. And then that's going to be a call.
We all know it's going to be the diagnosis from that AC/DC album. I'll let everybody at home figure out what that is. Anyway, okay. Keep going.
Yeah. All right. Okay. So, all right. I think I said evidence is present, but not always there. evidence is quoted without explanation, and evidence is misrepresented. I think we went through all of that. Okay,
Yep.
so look at those and then decide how you think they fit in there and give it a number, so that we
Yeah.
can give
Don't
us a
do it
score.
yet, people. We're going to go
Yeah,
over it.
you got to listen to the evidence first, all right? We're not going to be one. We're not going to be like them, all right? We're actually going to listen to evidence, and then when we've got evidence, then we'll make some judgment about it. Okay, all right. Okay, in 4, that's the tone and objectivity. So, in other words, is there objectivity? What's this tone like? So, is it neutral? Is it analytical? Is it focused on reasoning? All right, or is it occasional emotive language? All right, so that happens a lot in this discourse. Okay, but it's mostly objective, so we can give it a medium, maybe worth a 3. And then if it's low, in which case it's only worth a 1, it's frequent emotive or persuasive language. So persuasive language is a thing if you want that to be. So if I'm writing some persuasive piece, I certainly wouldn't be objective. Okay, I really do want to change your mind. Okay, I do really do you want you to buy this product. So I'm not going to be objective about it. I'm going to say, and at the end of it, I'm going to say, well, get to the shops and get that thing. Okay, so I'm going to be forceful about what I want you to do. I'm actually going to try and persuade you to do something, or persuade you to think like I think. So I'll use emotive language to do that. All right, that's not what science is about. I have to be objective. Okay, all right. The tone is sarcastic, ridiculing, or polemical. Sorry. Okay, I've got there. All right. So basically, it's mocking, if you like. Okay. So, or sarcastic. Okay. All right. All right. So if it is that, then, and as soon as somebody throws sarcasm like that into it, then then it's not being objective. Okay. Sarcasm has its place, and no doubt I will be sarcastic at times. All right. So, but not in grading. I won't be. All right. So be careful yourself not to be that person, not to be when you're grading. All right. In criterion 5, we're looking at the argumentation quality. Okay, here claims are supported by reasoning, examples, and clear logic. All right, medium, some reasoning present, but inconsistently applied. We would, if it's still there, we'd give it something for it. We'd pay something for that, and that would be a 3. And if it's low, the claims are asserted rather than demonstrated, or no evidence at all of it, then we'd give it a 1. But we would say there's some value in the claims, but they're not supported. We might give it a 1. But if its argument relies on rhetoric, emotion, or mischaracterization, obviously in that case we'd give it a 0. All right. So look out for things that are in that would be in argumentation quality, and then you can give it your score. Okay. All right. Okay. In 6, which is the last one, we're looking at the literary maturity. Okay, so whether or not the writing is clear, disciplined, purposeful, so we don't have metaphors falling out all over the place, sometimes missing, sometimes hitting, sometimes landing. It's disciplined. Things are in their right place. Writing is readable, but occasionally unfocused, so disconnected and disjointed. Then we might give it a 3. You're right. If it's repetitive, it's digressive or emotionally driven, then we might give it a 1 if there's something there. Writing is chaotic, theatrical, which happens a lot in this book, or dominated by rhetorical flourish. Okay, so from the Black Lagoon, whatever, words like that. Okay, we'd call that a rhetorical flourish. Okay, totally unnecessary in science writing. Okay, so that would be the 6 of them. All right, so now I've got a worksheet for you. All right, so not just that, and you can come back and look at this later. We're evaluating scientific writing quality. So in other words, it's learning how to do this. It's really important that when you're reading scientific writing, that you're able to make these judgments about what you're reading. Okay, and therefore you can be an informed person when you're reading, and you're not just reading something and then accepting what you're reading. So that's important. So it's important to understand how to do this properly. Okay, and certainly if you're in the position of grading other people and commenting on other people's work in a way that affects their life, then for sure you've got to learn how to do this properly. Okay. All right. So here we've got a bunch of questions. So you're going to identify one example of persuasive or emotive language in this chapter that we're reading. Okay, it's chapter 3, and explain why this type of language weakens the scientific writing. Okay, question 2, the chapter uses humor and ridicule in several places. It does, so it's telling you that. Describe one example and explain how it affects the reader's perception of the argument. So in other words, what's your perception if it says, comes out of the Black Lagoon or whatever, however the language it uses. Right, in question 3, okay, find a quote where the author uses scientific terminology and explain whether the term is used inaccurately or rhetorically. Okay, all right. Pardon me. In 4, so the question 4, the chapter includes many external quotations. Choose one and explain whether it has been integrated as genuine evidence or just simply used to create authority. Okay, so somebody said something, or here is a link to some university, and that's the sum total of the evidence that's there. Makes no explanations about it, and often some of these links, the author will just select a very, very small part of that, maybe a certain sentence or a paragraph, and then take that completely out of context. Okay, so not include the things that came before it or the things that came after it, and therefore it just becomes rhetorical. Okay, so I want you to do that. For question 5, I'd like you to describe one strength in the author's writing style. There are some strengths here. Okay, let's be fair about this. Okay, explain why I missed out an S over there. This strength does not necessarily make the argument scientifically credible. So even though there's some strength in there, and there's maybe something's worded in such a way that's kind of clever, but then does nothing to make the argument scientifically credible. So see if you can see anything like that, and see if you can recognize that kind of language. Right. All right. Let's move on. All right. For 7. I think we've been through 6. So 7 here, explain the difference between persuasive writing and scientific writing, using an example from the chapter. So we are all about what's in the chapter. So it's not something from outside that's external to this chapter. Okay. And then based on your analysis, write a short paragraph evaluating the overall maturity of the argument presented. Okay, so go over this video again. You're not going to remember all of these things at once, okay? And then see if you can do that, and maybe at a later stage in another video, we can go through these questions and discuss them. Okay, it'll be a bit of fun. Or we might do it might be not this chapter. Maybe we'll choose a different chapter. I think there might be a chapter on gases. That would be an interesting one to do. A chapter on gases.
There is, yeah.
Because I think that's the one that he throws in a whole bunch of laws. So he uses his text to go through different laws like Charles' law and Boyle's law and so like that, and completely mischaracterizes everything they say.
It does not relate. It does not relate at all. He doesn't do any of the actual application of those laws.
Yeah, just tells us what they are. Yeah, well, we learnt that like in about 8th grade or whatever.
Yeah.
Okay. All right. So that's your homework. Okay, if you don't mind doing that, and let's have some fun with that later on and see what people came up with. Okay.
Okay.
All right. If you can just unshare that for me, please.
Okay. There we go. I can. All right. You're still sharing, but I have you on screen because I can switch.
Oh, right. Okay. There we go. All right.
Yeah.
Okay. All right. That's good. All right. We're done. All right. So the next thing is
We could do if we could do a catch up on I got a couple things from the audience.
Yeah, yeah, go ahead. Yeah, please. Yeah. Good time to do that.
People are enjoying it. A lot of big fans for sure here. Some people
Good.
like names I haven't seen in a while are here just because you're here. So that's very good. Let's see. Mr. E-Man Original says, why can I not mark this work as? And that's the end of it. That's all he said.
Okay.
I don't know what that means. Did he not finish it? Scotty Orange, this is an interesting one. He says, any chance N, and I think N means Newton, any chance Newton secretly knew more than we know? And he had previously mentioned that Scotty suspects that Newton suspected that Mercury's unusual orbit was due to something related to whatever. He's left it a little nebulous, but that Newton maybe was a little too unsure to mention it.
I would think that that Newton, without a doubt, we're talking about a very, very, very clever individual, and there's no way known he wouldn't have thought about the idea of geometry. But Newton wouldn't publish something like that or venture down that without the ability to or the time to actually say how would that work in geometries. But I have no doubt that he would have probably thought about it. And you know, Newton he's the calculus guy, for goodness sake. So he understood. He, of all the people then who could do something like that, he was it.
Yeah, maybe the other geometries and things that Newton relied on from other people that had that came after Newton, if they were available to Newton, maybe he would have.
Yes, exactly right. So yeah, we're always constrained by by what's available. Like I said, only had 4-figure log tables. That's the best. That's the most significant figures I could ever get, and yet now I can get as many as whatever the calculator can handle. Maybe 8 significant figures.
Well, if you use the right library in Python, you can go more than that.
More than that, yeah, of course.
Arbitrary. Larry Scott says, is it on the surface? G equals 9.8 meters per second squared. At the center of the Earth, G equals 0. So G is the greatest at the surface. And that's correct.
Yeah.
The gravitons, I think a gravitational field, is centered at the center of Earth.
That's
and
right.
so I realized after I said it that I mischaracterized. I think I gave flat earthers a little bit too much credit. Flat earthers claim that gravity is maximized at the surface isn't that it's maximized at the surface. They claim that it should rise exponentially until you get to the surface because they don't understand the math at all. And they also, they're not thinking of it, Larry, as you are, that inside the Earth, because you have some of the Earth above you, accelerating you up as well as down, that's why what's causing it. They are thinking of it more like how Coulomb's law works, that on the surface of a charged sphere, the force is maximized according to Coulomb's law, not at the center of the sphere, because inside a sphere, if you just have a basic sphere, the inside of it is uncharged, and so Coulomb's law will give you net 0 on the inside of the sphere. Anyway, I may be giving them too much credit still. Hugh Jars. Go ahead.
No, it's all right. I want to here's my superhero, so I'll hear what he says.
Hugh Jars should be everybody's superhero. He's that big. Says, I am a big fan of Professor Phil, but then again, I'm a big anything. Phil knows I love him anyway.
Yeah, he is a big anything. So yes, no, I have a photo of me wearing one of his shirts, and it looks very cool.
At least not his onesie. Please no. CK Mamacita says, Professor Phil Bell, you're looking great, healthy, and I'm happy you are here with us. Thank you.
Oh, absolutely. I feel like a million bucks compared to where I was even just, a few weeks ago, a couple of weeks ago, a month ago, I was in ICU. So here I am talking to you. So it is pretty amazing.
That is great.
So no, coming a long way. Made very, very major surgery. Took out a tumor about the size of a fist. So that's pretty major surgery. Cut a lot of nerves and stuff like that. But and then had to face a an infection which nearly took my life. So now I'm back. All right, here for the long haul, Mr. Oakley. I'm coming for you.
All right,
I'm joking. You're just so meaningless. It doesn't matter.
All right. All right. Ready for your next portion here.
Okay, good. All right. Okay. So now we're going to have a look at the claims. Okay. So this is a bit of a fun part, this, looking at the claims. All right. So I'll close down my last one. Okay. So I'll click on that by accident again. Okay. All right. Okay, so let's run this slideshow from the beginning. All right, so I've got to share this time, remember? Okay, so here we go. And hit share. There we go. All right. Presumably you can see that.
Here it comes.
Okay.
All right, now we see it.
All right, so here, okay.
Yep.
So this is the gravity of the situation, which is the title of that chapter. Okay, from Welcome to Flat Earth, which is the title of the book, and the authors Stunya and Macon. And I have to say, I am really disappointed with the Macon part of it, because this is not an uneducated person. Okay. That could be the doctor now. Safety day, please. Okay.
I muted myself and him. Anyway, so it sounds like he is talking to to receive his diagnosis of the AC/DC song, if you know what I'm saying. All right. Oh my goodness, he's talking and I'm distracted. I can hear him, but I need to hear him when he comes back, so I can't completely not have anything. This is he's done a lot of work on this. I really appreciate this. He's going to go over now the things from the book that are being claimed, and then that will give us an opportunity to apply the rubric that he spoke of earlier. So keep that in mind, and if you need, here, I'll give you this. There you go. There is the I took notes. Apologies for my somewhat sloppy handwriting. I've spent basically my whole professional career typing on a keyboard and not writing by hand. So there you go. Icy Spin says, does a helicopter fly with 1,000-mile-per-hour wind? Checkmate. Checkmate. Of course. All right. I think he's wrapping up.
Okay. All right. So ready to go again.
All right. Good timing.
Okay. So yes. So that wasn't the doctor. That was another one of those people. So they send me some lymphedema garments, because that's one of the side effects of having having your lymph nodes removed.
Oh.
Okay. So basically, your lymph nodes drain fluids from your muscle and so on. That's what they're there for. So they drain that away, and then they end up as waste. But if you don't have lymph nodes, there's nowhere for all this fluid to go. So it builds up in your body, builds up in your leg. And what we're trying to do is use compression garments to actually try and force them to go in a particular direction, and then hopefully the body then works out different pathways to for the drainage, that because it doesn't have lymph nodes anymore to do that with.
Got it.
So we're learning some biology as well. Okay. All right. So the gravity of this, so here it is. So what are we doing? We're passing a flat Earth chapter's argument that gravity does not exist. Okay, which is that. And then we're going to go claim by claim, naming each fallacy and weighing it against the evidence. Okay, so let's have a go. This should be fun. Okay, so here we're saying the trick. That's the sleight of hand runs through the whole chapter. Okay, all right, and the argument depends on quietly swapping 3 different meanings of the word gravity. First of all, the phenomenon. So things fall, planets orbit, pendulum swing, observed, measured, and undeniable. Then we've got a force. Okay, Newton's useful model of that phenomenon. That's a pull between the masses. Curved space-time, Einstein's deeper model of the very same phenomenon. So that's what we understand. But the trick is muddy or disprove models 2 and 3, and then announce that phenomenon 1 isn't real. So that's what they try to do. So see if you can make pretend that we say that that there's no force, that there's no such thing as curved space-time, and therefore gravity doesn't exist. 1 doesn't exist, and that's the trick. Because I mean, of course, regardless of 2 and 3, 1 is measured. Things do fall. Planets do orbit. Pendulums do swing. We observe them. We measure them, and we can tell that things that fall accelerate at the same rate. Okay. Right, so the better explanation of why apples falls has never once stopped an apple from falling. Okay, the phenomenon does not belong to the model. That's the key. Okay, all right. So equivocation. So that's what else does it do? There's 6 moves that they use over and over again. Equivocation being one. Swaps the phenomenon for a model mid-sentence, and then attacks the model. We've got quote mining to the right. Okay, so physicists' words about mechanism clipped off the context that affirms gravity. So just okay. So George Musa says Einstein overtook Newton, and then gives it no context at all, doesn't tell us where and how and where, which part, just uses that, just takes that clip and says this is what he said, and therefore he must be right. Never mind that in his very next breath says that the Earth is a sphere. So let's just forget about that bit. So as long as he said the thing that we wanted to say, take whatever he said completely out of context. And that's the rule of thumb for the flat Earth community in general, and most certainly in this particular text. Okay, so superseded is equal to debunked. Again, harking back on that. So I said something superseded, therefore the other thing didn't exist. That is the logic, if you want to call it that. That's used in this particular text, and certainly in the wider community of flat Earth. So that treats Newton to Einstein refinement as proof that the subject is fake. Okay, then private redefinition. So redefines pseudoscience. That's his own version of what that means. Redefines experiment. Redefines phenomenon. And then declares victory over the whole of all of those. And in fact, is arrogant enough to say astronomy and geography and all these things are not science. Okay. Okay. So genetic fallacy. Okay. So this attacks who named G, for instance, built. So saying, well, Cavendish didn't build the apparatus. He didn't design the apparatus, so therefore it's all fake. So we can't count anything because Cavendish didn't do it himself. And in fact, this is a common theme throughout this book, in other chapters. You need to have done this yourself in order for it to be, otherwise it's automatically fake. All right. Never mind, other people have done it. It's got to be done by a particular person for it to be true. All right. So that's ignoring the evidence. Okay. Never engages GPS, for instance. We don't need that. I just say, oh, GPS is balloons. So they'll say, oh, these are just high altitude balloons that are going around, or satelloons, they'll call them. All right. When is one of these people, when is Macon or Stilja going to ring TomTom or Garmin or one of those people and say, could you please tell us where the data comes from? That should be enough. The people who make the satellites, the people who use the information from the satellites to make receivers, well, they know where the data comes from. I've got a satellite dish on my roof, which I've had for 12, 15 years now, and the satellite dish points at 37 degrees towards the equator. Now, I worked it out. If this was pointing at a tower anywhere where I live, and it's pointing at 37 degrees, then that tower would have to be 150 kilometers high.
Well, that's quite a tower.
Yeah, that is quite a tower. I mean, let's face it. Okay, so we'll come to that in a bit. But the writers of this book, and you would think, well, okay, if I make a claim about a particular thing, in other words, that my dish is pointing at a tower, then there are consequences for that. And one of that is there has to be a tower of X amount of height. So if there's a tower in my city, it's going to have to be a very, very tall tower in order for that to be true. But they never take it to that part. They'll hone in on one particular thing, think that they've got a victory over that one particular thing, and not realize that making that claim has lots of other consequences. Okay, so for instance, to ignore GPS, ignore the spacecraft, just pretend they don't exist. So those things that are traveling in a straight line in a straight line across the sky, let's just pretend they don't exist. They balloons. Maybe they call satelloons. Well, really, they're traveling at more than 10 times the speed of a fighter jet, all at perfect single file, right through the jet streams, and they're perfectly straight. And not only that, if you wait, they'll be over another country in just 40 minutes time. So let's say they're heading south. All of a sudden they're coming up from the north, heading south again, for just 40 minutes later or 90 minutes later, however close to the south you are when you see it. I mean, you have to be a human who has no powers of deduction to be able to deny that is a phenomenon that's worth considering when you are talking about your flat Earth. Okay, then there's LIGO, and then there's tides. You know, what happens on Earth. So the standard thing for them to say is, oh, water's flat. All 72% of the water around the Earth is flat. How is it flat if there's practically no water over here because the tide's gone out, and a king tide over there? How could the water be flat if that was the case? So just little things like that, just making those claims, which children could debunk. Okay, right. Let's move on. All right. So here we have claim number one. Okay, claim number one. Which type of gravity? Newton's or Einstein's? We've kind of spoken about that before, but let's go. There's a false dilemma. Okay, and then superseded is, and their claim that superseded is equal to debunked. Because Newton and Einstein described gravity differently, then the very idea is incoherent, okay? Forcing you to pick one, supposedly exposing the fraud. So they're saying, well, that's pick one of those. Is it Newton? And that's a frequent thing said by these two authors themselves. They'll say that on their show many times over, and they certainly say that in this text. Okay, and then why does this collapse? Okay, so that it collapses for the same phenomenon, different mechanism, but both describe the identical observations. Okay, and agree to many decimal places in everyday conditions. Right, they differ only in the proposed cause. Okay, one didn't have a cause, the other one had a cause. That's really where the difference lies. Okay, so Einstein contains Newton, right? So gravity relatively mathematically reduced to Newton's laws, okay, in the weak field and low speed limits. NASA still flies spacecraft on Newtonian gravity to pinpoint accuracy. In fact, all the spacecraft, none of them would, no spacecraft's going fast enough for us to consider using Einstein's one. So Newton is what we use to get spacecraft to actually work and to get satellites in orbit and all those sort of things. Okay, so refinement is not refutation. So replacing a flat map with a globe doesn't abolish the contents. Okay, a sharper model of the cause never erases the effect. So mark that particular quote. All right, the bottom line: two models converging on one reality is healthy science. It's not a hoax. Okay? It's what we expect to do for science. Claim number 2: gravity is an abstract concept. Let me see. That can't be proven. So it's pseudoscience. So as long as you can't prove something, there's no proof, then it's automatically in their book pseudoscience. Although this book says I don't know. So they automatically debunk themselves by saying, well, therefore, if you don't know, then it must be pseudoscience, because that's what they're saying generally for the mainstream people.
Yeah.
Okay. So why is it?
They don't like to apply their own rule to themselves.
No, exactly. So why does it collapse? All right. Well, gravity is measured. It's not assumed. Okay. Drop anything and check the acceleration. G equals 98.8 meters per second squared, or thereabouts, depending on where you are. Okay. And reproducible by any student anywhere on Earth. Okay. So this is a phenomenon. It's not a vibe. We can measure it. Okay. We can see it. The planets actually go around the sun. We can measure it. The Earth goes around the sun. We can measure that too. Okay, this isn't up for debate. Like Whitson said, there's this equivalence. How is it equivalent if the planet takes a few years to get around the sun, and that same sun takes only 24 hours to go around once? What's this planet doing when it's halfway around? Where's this planet when it's halfway around? I mean, you can't dispute the fact that the planet goes around the sun. We can measure that. We can't dispute that all the planets go around the sun. So all the planets are following the sun. How could they be doing that if they take years to get around the sun once and the sun takes only 24 hours to go around once? Why is that not something that's, hang on, that doesn't work? How much intelligence do you need just to work out something as simple as that? Put those two propositions to a child and they'll figure it out. That doesn't work. Okay. All right. So science confirms the phenomenal constantly. Observations and measurements are exactly how existence claims about to measure. I should have got that sentence right. About measuring things get tested every day in every lab. Pardon me. Okay. So their definition, fits the chapter, not gravity. A claim of scientific validity that skips the scientific method. described as an argument that ignores all the measurements far better than it describes gravity. That's one of the main things to say. Well, that didn't fit the scientific method. You didn't have an independent or a dependent variable, or something else. Therefore, it's not science. Therefore, it's fake. It doesn't matter that you measured it. Oh, let's just forget about that part. Okay, that you measured it. And by the way, if they go and measure something, that's true, even though it doesn't meet their criteria for being science either. Okay, so what's the bottom line? You can measure it to many decimals, okay? And the opposite of an untestable abstraction. That's the opposite of an untestable abstraction, the fact that you can measure it. And that's a thing that's ignored all the time, and it's certainly ignored in this text. Okay, claim number 3, even physicists admit gravity is not a force. This is the one that actually makes my blood boil, this one actually. Okay, so that comes down to quote mining and equivocation, which is false. So Brian Cox, this is a word for word. I didn't write this. Brian Cox, D-E, sitter, and textbooks all say gravity is not a force, so it isn't real, and NASA is 111 years out of it. This is a quote from the text. Okay, so I didn't write that. Okay, all right. Why does this collapse? Even if you could understand what it means. Okay, not a force is about mechanism, not existence. Relativity says gravity is better described as space-time geometry than as a Newtonian pull. So in other words, it's not something that's pulling, that the effect that geometry produces is precisely what we call gravity. So a gravitational field. Okay, so we shorten that when we say gravity, we're talking about a gravitational field. Okay, so every physicist quoted affirms, well, this is every physicist's business thing. When is one of those physicists going to come out and say that the Earth is flat? Okay, and believe me, I need to talk to that physicist who comes out and says the Earth is flat, if there ever is one.
Well, even more than that, any physicist that would read his chapter on gravity and say, yes, you quoted me and I agree with how you presented the whole thing.
Precisely.
No, it's cherry picking and quote mining such that the people that they quoted would disagree with them. Yeah. You're just trying to use their mouth to present your lies.
The latest thing I've heard is that William Shatner has said that the Earth is flat. He went to space, remember?
Yeah. I saw that video, and I think it is fake.
Yeah. So there you go. Again, complete nonsense. All right. So force remains a valid working description. So engineers use it to land probes on other worlds. Okay, and 2 descriptions, 1 reality, both correct in their domain, in their own domain. Okay, so the bottom line, gravity is not a Newtonian force, means it's geometry. Doesn't mean it's fiction. Okay.
They also like to not understand derived forces like centrifugal acceleration and centrifugal force, right? If you're in a car, the car turns, you get pushed to the outside of the car. If you had a spring, and you know, could you do work with that spring within your turning reference frame? Yes, you could do work with it. So that doesn't mean because it's a fictitious force that it doesn't exist. That means that it's derived differently. You can still do work with it. And
yes, of course.
Flerfs when we say do work with, they don't even know what that means.
Yeah, correct. Well, I think I could actually show them a simple example of how that could be, and that is drop a house brick on your foot and then tell me that you think there was no force involved. Okay? Okay. All right, good. Let's move on. All right, so actually, I think I missed the bottom line of that one. Because I think so. It said, we did that one. Okay. All right. Number 4, the Cavendish experiment is a flawed parlor trick. Another one of God. Okay, that's a genetic fallacy, moving the goalposts, and self-refuting standard. All right, so what do they say? This is a quote, okay? It presupposes a debunked force. So here they've taken the mischaracterization out of one place, and they're now sticking in somewhere else, and then passing it off as fact. Okay, so they mischaracterized it in the other place, as we just pointed out. Okay, and now using that mischaracterization in this particular quote, and then passing it off as fact. Okay, so a debunked force only measured density, had no hypothesis, and used a man-made rig. So it's not real science. So let's break that down a little bit, and then
The
we'll go
man-made rig. Oh, I love that.
yeah. Okay. So just looking at that, and we're saying, well, it had well, hypothesis is actually quite simple, and that is that you take a guess that this thing causes that thing to happen, or that thing is related to that thing, doesn't have to cause it, and then you make a prediction, and then you design an experiment to test that and to see if it's true or not, and then if it isn't, then go back to the drawing board. If it is, then you've gathered some evidence, not proof. You've gathered evidence. Okay, when you've got enough of this evidence together, then you can say, I have a high degree of confidence, and that's what we rely on. We don't talk about science as being proof. We talk about science as in terms of our confidence. So it happens so many times. It happens all the time. We can't get it to not happen. We pretty have a high confidence that that's how it works. Okay, we don't say this is proof that it works. We talk about our confidence in it and its ability to make accurate predictions, and that's the most thing, and that's why we need it. That's why we have it. Okay, so why this collapse in that debunked force? Newtonian gravity is limiting case, not an error. It's just a limiting case. Okay, and the fiber physically twists. That's a fact. Why did that fiber twist? Okay, it physically does. You can't object. You can't object to that. Okay, so the deflection is the observation, whatever model explains it. So maybe you don't know why it happens. Maybe you don't know why this thing got attracted to that one, but it did. It twisted the fiber. It gave us the evidence that it does happen, and therefore. It opens the door to working out, well, why? Why did it happen? Okay, and then thankfully we had Einstein to give us an explanation for that. Okay, so measured density, not gravity. You can only get Earth's density. So this is, again, I think referring back to Cavendish, they were saying, well, he wasn't measuring gravity, he was measuring density. Okay, all right. So again, just not understanding that there's things vicariously that you can get by doing that experiment in order to learn that particular thing, and then by doing that can make some deductions about the thing that you're actually after. All right, so it measures gravity directly. Density is what you derive, okay, afterwards. Density, we got density. I think they kind of forget that density is just a mass and volume relationship.
Yeah,
has nothing to do with acceleration. Nothing to do with movement at all.
So the Cavendish was seeking to measure the density of the Earth, and you mentioned it earlier, 5.4 times the density of water, 5.4. And that was his goal. But in the process of doing that, he accomplished a bunch of other things, including outputting the gravitational constant.
Yes.
Inadvertently, it wasn't his intention, but it's there.
Yep, exactly.
So he did measure he did measure density, and he measured gravity.
Okay, so the no hypothesis, its hypothesis was precise and falsifiable, a two important thing. Okay, so two masses attracted by a calculable amount, and the beam deflected by very nearly that amount. So it matches what we make a prediction, and then we design an experiment that should work if that prediction is going to be right, and then it does. Okay, so just a man-made rig. So again, Studio in particular, I think he probably introduced this to this, and certainly writes that in his book.
Yep.
and talks about natural science. So he never says the word science. He always uses the word natural science, as if, as if that then means
There's flavors.
any other
Yeah.
kind of science you do. It is not science because it doesn't involve something that's happening in nature. So if I add two chemicals together, let's say I want to synthesize an alcohol, for instance, and I'll do I'll use sodium hydroxide to displace a chlorine atom, and then I make an alcohol. Well, that's not science anymore. That's because I had some test tubes and I had some, apparatus. And all these things are all man-made, so it can't be science. I mean, how ridiculous is that? I've made a prediction. If I have a haloalkane and I add a hydroxide to it, I'm going to displace the halogen out of that and create an alcohol. That's my prediction. And then what happens? It does work. It happens. So what does that say about all the things that I assume about that I know about the atoms, the way they behave, the way alkanes behave, the way haloalkanes behave, the way alcohols are formed? What does it say about all those things? It is clear evidence that all of those things are right. Okay, it wasn't magic that came up with that. I made a prediction, and I made an experiment to test that prediction, and it came right. It came true. So that's science. That's all we need out of science. And science can just be measuring something, can just be observing something. I make a prediction that there's going to be a planet out there based on all the stuff that Newton's done. There's going to be a planet. Then you go looking for one and you find it. How is that? That's not magic. That's using that information. That's making a hypothesis about what you'd find, and then actually doing the work, and then you find it. I mean, how can he ignore this? How can this author ignore that? That's a rhetorical question. Okay, so why does it collapse here? All right, okay, that's debunked force. Okay, all right, I think we went through this, yeah? Measure density, not gravity. You can get Earth's density by measuring the attraction between known masses. So it's a whole bunch of things that we came just because of measurements. So we can tell, because we know, for instance, in Kepler's ratio, the square of the period over the cube of the distance. Okay, because we can do that, we can predict. If we didn't know how far the moon was, we most certainly would be able to work out how far it is using this ratio. And that ratio works for all the planets, for all the satellites, for everything that we see that's moving. Thanks to Kepler's laws, these things actually work. So therefore, we can now make predictions, which we do, because satellites just don't go, I think I'll just put it over there. No, you've got to figure out what job you want it to do. If you want it to be geostationary, in other words, stay in one place so that your TV can work all the time. Okay, so you don't get TV for 2 seconds and then it's gone. All right, so you want your TV to be on all the time, all 15 years of it. Then it's got to stay in one place. Well, how's that going to happen? Okay, well, then the satellite's got to move at the same rate, at the same speed that the Earth is, right? And be at a certain position. So R cubed, it's got to be right. Center of the Earth to the center of the satellite, that's got to be right. Okay, and then the other thing about it is the period T squared. So that's the 24 hours squared. So put those two things together, and we now know, before we do any kind of work on it, you got to have it 36,000 kilometers. It's got to be there. It's got to be over the equator, 36,000 kilometers and away, and it's got to be moving at this speed. Well, it will be moving at that speed if you did. Okay, so what are you going to do? You're going to put the thing on a rocket, make sure it's going at the right speed, make sure that you get to the right to the right orbital range, and then let go of it. There you have now a geostationary satellite. Okay, that's how that happens. All right. The no hypothesis, another one of the things that drives you wild, and you think, oh, these people are just, you know, I'll try to be kind. Okay, no hypothesis. Okay, its hypothesis was precise, okay, and falsifiable, and that's the thing. It's got to be falsifiable. All right. By saying there's a dome and you can't falsify it, well, I suppose you can, but let's say you couldn't. Let's say you had no access to the things we do have, and therefore you could falsify it. Well, that's nonsense. That's just useless. That's the very definition of what he would call pseudoscience. Okay, just a man-made rig. Again, we discussed that. All right. So what's the bottom line on that? Newton doubted the cause and affirmed the law. There, right in that sentence, says it all.
Yeah.
Okay. Even though he doubted the cause, he affirmed the law. We don't call these things a law for nothing. Okay. The chapter quotes him to mean the reverse. That's what this chapter is doing. So, in other words, it's saying exactly the reverse. It's saying Newton doubted the law. Okay, and then affirmed the law and doubted the doubted the cause. Okay, all right. The chapter quotes him to exactly opposite to what he meant. That's what I'm trying to say. All right. Here we go in claim number 6, F equals G M1 M2 over R squared isn't Newton's. Big G is a bastardization. You have no idea. You don't know anything about mathematics, even by saying something that dumb in your actual. You actually wrote that and put your name on it.
Oh,
For goodness sake, you may as well write idiot on your forehead and go around saying, "Look how good I am," with idiot written on your forehead. Okay, that's about a good analogy for what they have done here. They've actually written that quote and then put their name on it. So genetic fallacy, irrelevant, pedantry. So, okay, so what do they say? Word for word. Okay, Newton only wrote proportionality F proportional to M1 M2 over R squared. Yes. Okay. Good. That's what he wrote. Okay. The constant G was inserted centuries later. Well, we're going to get an equality, so we need to have a constant of proportionality. So of course we're expecting to get one. Now it behoves the scientists to come afterwards, after Newton, and say, well, okay, let's figure this out. Let's figure out what the proportional. That doesn't mean Newton didn't know, all right, what that was. You knew what that was, but he didn't design an experiment to work out what it is. So Cavendish came along, worked out and designed. Well, John Michell worked out an experiment that would work out what it is, and Cavendish carried it out. Okay, so why does this collapse? Okay, proportionality and an equation are the same relationship. So you think, well, one's got this alpha symbol, one's got an equal symbol, so therefore they're wrong. That's the mind of this author.
He spent pages on this.
Yeah, exactly.
Pages on this misunderstanding of his.
Exactly. And so and then put his name on it and
embarrassing.
On it. Yeah, totally embarrassing. All right. Okay. Already implies a constant just by the fact that it says proportionality. So G merely fixes those units exactly as Hooke's and Coulomb's laws do the same thing. Okay. All right. So they're all happy with Coulomb's laws. Didn't like Newton, even though they express the same kind of relationship between those variables. Okay, so here it targets a footnote, not the phenomenon. Okay, even granting every naming quibble, it says precisely nothing about whether things fall or orbits hold. Okay, the bottom line: who measured the constant is trivia. Okay, the relationship still predicts the orbits, as an example. Right, 7. Okay, the laws of physics is an oxymoron. Their words.
Wow.
Yeah, yeah. And
And
maths isn't science.
and he will later talk about and use laws of physics to try to debunk the globe.
Exactly. Laws of physics is an oxymoron, they say. All right, so laws only describe and involve no experiment. Maths isn't science. Okay, that's and quotes, and so it's just taken. Forget the other words. Feynman didn't say that his maths isn't science. Feynman did say that, and Morse did say that. So scientific laws are contradictions, and only natural laws exist. Like I was discussing that before. And look at the writing here. Natural, uppercase N, laws, uppercase L. It's just childish. Okay. Wide comb. So I think maybe he thinks maybe there's an emphasis if you put natural as if it's a noun that you have to instead of an adjective. So the person doesn't even know how to write, much less write in scientific writing. But we'll cover that later. Okay, so why this collapses, the law and the theory distinction is being weaponized. Okay, laws are established by observation and routinely tested. Okay, describing rather than explaining doesn't make a law non-scientific. Okay, maths isn't a natural science. Well, if physics isn't a science, pure maths isn't empirical. Physics uses maths to describe tested findings. How else could you do that if you didn't have maths? How far could you get? You certainly wouldn't be able to make the predictions if you didn't have the maths. Okay. The argument slides between the two senses. Feynman wrote all of physics in maths. That doesn't even occur to them, to these authors. Feynman used maths to describe the physics.
Yeah. You can't invoke Feynman to reject using math in physics because he greatly used math and physics. It's just ridiculous. It's juvenile.
Yeah, it is juvenile. And if you examine this piece and the book in general, but this chapter in particular, what comes out of it is if you denigrate maths, you do that because they can't do maths.
Well, yeah.
So you need to throw the maths bit out. Okay? Because as soon as somebody challenges you on the maths, you're going to fail. Because if you tie the physics and the maths together, then you can't do most of it. Okay, so yeah, all right. It concedes the point it's trying to deny. I think that's obvious. Okay, it grants that natural laws describe what nature does always. Okay, right. Things falling towards Earth is exactly such a regularity. No gravity qualifies on their own terms.
So gravity. You said no.
Yeah.
Yeah.
All right. Yeah. So gravity. Sorry. So gravity. Yeah. Okay. So bottom line. Okay. A semantic shell game can't make a dropped ball hover. Okay. Let's move on. Okay. There's a couple more to go. That's all. So general relativity is pseudoscience. That's another claim. Really? And you put your name to that? Okay. False premise, category error. I like that word, category, those two words, category error. Right. GR contains no hypotheses. Okay. Was superseded by quantum mechanics within a decade and contradicts the uncertain.
Oh my goodness.
None of those are understood at all by the authors of this.
Oh.
They wrote absolute nonsense. Okay. Why does it collapse? All right, so let's examine it critically. No hypothesis is simply false. GR was made bold, risky, numeric predictions. They certainly did have hypotheses, and they certainly did have them tested over and over and over again. Like, for instance, Mercury's 43 each per century. Okay, sorry, I put the each there so people understand it. Okay, light bending,
Arc second.
1 point. Yeah. Second. Oh, no, sorry, they're seconds. Yeah, seconds. Right. 1.75 seconds. Okay. Redshift, time dilation, gravitational waves, since confirmed. Okay. Several to spectacular precision. Okay. Right. Yes. Yeah, that's right. It's seconds. It's angles. Okay. All right. So quantum mechanics didn't supersede it. Okay. Quantum mechanics and GR describe the different domains. Okay. Tiny scales versus gravity and large masses. Okay, all right. Both are load-bearing pillars of modern physics, used and confirmed daily. Right. So the GR quantum mechanics tension is an open frontier. This is one of the things that this book and flat earthers in general will working and talking at the frontier, at the cutting edge of science. These are people who can't do basic trigonometry, deciding that they have the skill to actually to actually argue at the cutting edge of science. This is kind of like this, right? Okay. GPS runs on quantum clocks, okay, and general relativity at once. Okay, every single second. Claim number 9: you can't bend space-time. It's only a concept. This is another thing. Okay. Right. I think we covered this, so I'm just going to go past this. Okay. Space and time are abstract and non-physical. Can you bend freedom? What has that got to do with anything? Okay. Calling. Think about the rubric when you listen to that, the language. Okay. So calling space-time warped is a reification fallacy. Why? Why is it a reification fallacy? Okay, all right. I'm not going to go through all of that. You can read this if you like. I'm just going to go to the bottom line. You can't measure the bending of freedom. Big deal. So how has that got to do with anything to do with space-time? How's freedom and space-time the same thing? Okay. We do measure the bending of space-time. Okay, last one. Okay. We don't even know what energy or mass is. Is in capital letters. Okay, this is in a book. They put their name to it. Okay, I didn't put the capital letters there. They did. All right. Okay. Proves too much. Okay. Demanding ultimate evidence. They say. Feynman says we don't know what the energy is. Wheeler and Bourne say similar of mass. So gravity has no real grounding. So this person and that person say they don't know what stuff is, so therefore the stuff doesn't exist. Don't know what that train of objects is flying in the sky that's going 10 times faster than any fighter jet. So let's just pretend they don't exist. That's it. That's the logic in that statement. That's exactly what that logic is, or illogic. All right, so why does it collapse? Not knowing the ultimate essence never blocks measurement. Energy is conserved to extraordinary precision. Okay, all right. Mass is measured every day. Okay, precise prediction doesn't require metaphysical certainty. What's mass? Mass is a measure of something. Well, you can decide that it's a measure of your ability to move something, or inertia. So it measures it's some way that we use to measure particular things and compare it to other things. So if I move the mouse, I move the glass, I require a different amount of energy to move that mouse and that glass. What's the difference between those two other than, their shape and everything? Their mass. That's the thing that we measure. So now I can measure the mass of both of these things and I can make a comparison. And then I can use that comparison to decide whether how much energy I need to move this compared to how much energy I need to move that. That's what we're talking about. That's why we use it. We use it to make those sort of comparison. And one of the things about this that's not mentioned in this particular text, and that is, regardless of how much energy I need to move that or to move that, if I drop them, they'll fall at the same rate. They'll accelerate at the same rate. Completely ignored in this. Okay. The same is true of electric charge. Nobody knows what charge ultimately is, yet all electrons work, right? Applied consistently, this argument deletes every science, including any of the authors, any of that this actual author does accept. Okay, defined by formula is a strength, not a flaw. Okay, Born's point is operationalism. Okay, defining a quantity by how it's measured and behaves is exactly what makes it scientific. This is always a case in point about science, and that is we can't necessarily, for instance, I have to find out whether or not I have an infection. Okay, so I could go through another stage where you chop it all open, take out some cells, look at them under a microscope. Oh, infection there. Well, that could be one way. Or another way is I could measure the CPR in my the marker for my liver. The liver expands when it's got to deal with when your body's got to deal with an infection. So it inflates. Okay. So that change is that change in your liver is actually measured as a marker in your blood. So there are certain markers in your blood that point to that particular phenomenon taking place, and that tells you that the reason for this happening, this inflammation, is because of an infection. So the CPR tells you there's an infection. So the CPR tells you there's inflammation. It's the inflammation there that tells you that you have an infection. Use that with your white cell count. Put the two of them together, and you can now have a picture. Do you have an infection or not? Okay. So, and there's a whole bunch of other things, of course, you can measure, like your temperature and all that sort of thing. But you put all of those things together, and so none of those things involve actually cutting you open and checking to see if there is an infectious cell there. You don't need to.
You don't have to go there.
No, you don't have to go there. Okay. All right. Okay. All right. Where were we? So, okay, let's move on. So an argument that erases all of physics hasn't refuted gravity. It just refutes itself. All right. The case it forgot to address. This is important. Okay. All right. This is the last slide. Okay. The evidence that the chapter never once mentions. Free fall. Anywhere, they never mention it. Okay, G equals 9.8 meters per second squared on average. Okay, reproducible with a stopwatch. You can measure it. Okay, it's not a thing that maybe it's this, maybe it's that. We measure it. In fact, we use that measurement in order to make predictions about minerals, how far the satellite's going to be, what it's going to do, how long is it going to be before this a meteorite comes back again. By the way, I have yet, if Mr. Dick Wayne is in your audience, could you please ask him? Where does the comet hide for 76 years, and then who puts it up there so that we can see it again? Underneath this dome, where does it hide? Who's got it? Who's got that comment? Or does it just get off by itself?
It's never, if it's above flat Earth, there's never anything between you and it, so you should never not see it.
Exactly right. Well, it just appears in the sky, so it obviously came from somewhere. Where was it? Where was it before we saw it in the sky? Like, like there's like 76 years or something in between it. Where was it? Where was the meteorite before it ended up in the sky that we could see it? Where was it hiding under the dome is what I'd like to know. And obviously it got into the sky somehow. It needed energy to get up there into the sky. How did it do that? Oh, we don't have to answer that question. That's the answer from the flat earthers. They don't have to answer that question. We don't know.
Yeah, they think that
Okay.
don't know beats having solid answers. It doesn't. It
exactly.
doesn't.
All right. Okay. Hammer and feather. That the one on the moon. Of course, they're going to deny that. We saw the hammer. We saw the feather fall together. And of course, there are other experiments done on Earth that show that this is the case where things fall at the same in a vacuum. They're going to fall at the same rate. Spacecraft navigation probes landed within kilometers. Okay, after billions of kilometers. I mean, so accurate, so that it can make really, really very, very accurate calculations, so that that spacecraft stays right where it is. When this technician came around to install this satellite dish, and I offered to help him, and he was great because it meant he didn't have to get down the ladder, go to my TV, adjust, check to see if it was right, get up the ladder again, adjust again. He had somebody he could yell at and say, "Yeah, yeah, okay." I say to him, "All right, move it, move it. Oh, yeah, spot on. Just leave it there." Okay. And he was really happy with that because he didn't have to go up and down the ladder to do that. Well, it was just like a centimeter out, or maybe less than that. It was like millimeters, where we had to get this right in the right place. Otherwise, there was no signal. And that kind of makes sense because a tiny little angular change over here, okay, when we're looking at something that's way over, that's 36,000 kilometers over the equator, that's a huge difference out there. Okay, I'm not sure if the flat earthers are smart enough to figure that out, but there you go. Probably not. All right, because if they were, they wouldn't be flat earthers. Okay, GPS only works by correcting for relativity. Again, as I said before, it's got the two things. It's got general relativity. We've got to worry about that, and it's also got it also has time dilation. So those two things have to be factored together. Subtract one from the other so that you can get the time correction. Okay, and again, tiny little bit of time on that satellite is a huge distance on Earth. Okay, ocean tides. Forget about that evidence. I say, oh, gravity doesn't know. Oh, so what does then? I don't know. Then how do you know it's not the gravity? I don't know.
I love the tides.
Gravity doesn't exist.
Because of what Dubé said. It's the rising and falling of the bosom of the deep. I just like that he said bosom.
Yeah. That's yeah. Okay, it's Mother Nature. You've got to put Mother Nature in there. So Mother's got the bosom. All right. So gravitational lensing. Forget that exists, even though we have evidence for it. Okay. All right. LIGO. They just spent the billions of dollars for nothing, right? Just so that we can trick a handful of stupid people. You spend billions of dollars to trick a handful of stupid people. Almost every other day, a rocket is sent into space to deploy satellites or one thing or another, almost every other day. And yet, even a cheap one, $150 million. $150 million. What? Just to fool some silly people. The arrogance is astonishing. Okay. The Pound Repka in 1959, the gravitational redshift measured in a tower. Okay, here it is. This was the first successful laboratory measurement of gravitational redshift. and it's a key prediction of Einstein's general relativity. It showed that light loses energy, in other words, redshifts, when traveling upwards in Earth's gravitational field, and therefore when it's falling, it's blue shift. Now, for those of you who don't actually understand what that means, because obviously the authors over here didn't understand it. So when we talk about redshift, so if you have a look at the middle band, okay, so if that's where it is in the middle band, these here are a particular distance apart. They're like a fingerprint for an element, and say for an element that's one of the elements in light that we've noticed. For instance, we can see that the highly energized element that's from the star that produces light would be hydrogen, for instance, okay, and helium. So then we can see over here that's how it normally is, okay. And then if it's redshifted, then you'll see that these bands start heading towards the red area of the spectrum. And then if it's blue shifted, they start coming back towards the blue area of the spectrum. And we can tell that which direction they're going in. And this experiment showed us that if it's losing energy, in other words, it's getting up higher, okay, then it shifts towards red. And if it gains energy, then it shifts towards blue. That was predicted. Pounded Repka decided to put that together in an experiment to see if it's true, and then again confirmed not just gravitation, but confirmed Einstein's view of gravitation. Okay. That's the end of the claims, right? So here, what's really on trial? Okay, what the chapter actually demonstrates, it never touches this phenomenon. Every argument targets a word, a model, or a piece of history. Through all of it, things keep falling, even though no matter what they say, things fall at the same rate, in the same place, regardless of their mass. Okay. The method is rhetoric, not measurement. By the way, we'll get a chance at some stage to talk about why things rise, because that's the other thing. Because so they say, oh well, why does helium go up? What's that? We thought everything falls. Well, if the helium was cold enough, so that would be about around minus 140 or so degrees, not degrees, Kelvin, then the helium wouldn't rise. It would fall. Okay, so it's obviously related to the energy that it has, whether or not it's got the energy to move around fast enough so that the energy overcomes the gravitational field force that's there. All right. The method is rhetoric, not measurement. So redefine terms, mind quote, name Latin fallacies, and often misspelled in this text, and never engage a single number. All right. So no alternative is offered. Okay. It never explains why things fall, why orbits hold, or why G is measurable. It only renames the question. And that's a typical thing. So if you want to hear somebody ask questions like that and never actually land on any of them, that's that Angel silly guy, that Aussie. I'm ashamed to say he's an Aussie.
Yeah.
Okay. All right. So we have our own idiots here. Okay. All right. Okay. By its own admission's fatal. It grants that natural laws describe what nature does always. Falling is exactly that. Acceleration when it's falling is exactly that. So you concede that gravity is there. So you'll hear silly people like Flatzoid saying, well, just call it pink devils or whatever he says. I don't care. You can call it whatever name you like. It's accelerating. It's falling. It's accelerating. And you'll need a force to stop it from doing that. You'll need something. When it does stop from doing that, it's going to exert a force on something, on the thing that you're asking to stop. You hold something up, okay? You can hold something up. What you're doing is you are exerting a force that's greater than the gravitational that's required to fall down. If you're sitting in your chair, okay, you can actually feel that you're pressing down on the chair. Okay? You're causing something to pressing down. What happens if we remove that? You're going to keep going down, aren't you?
Yeah.
And something else is going to stop you, like the floor. If you have enough energy, you can rise. That doesn't mean that gravity doesn't exist. Doesn't mean, oh, the bumblebee, or whatever it is. The bumblebee is flying, so it's overcoming gravity. Well, it has more energy than the gravity that's needed to make it fall. Why don't you just kill the thing and see if it doesn't fall? Stop it from flapping those wings around. What'll happen to the bumblebee? Won't it fall? We're talking about stuff that little children would be able to understand. So if you are out there and you're listening to this and you are a potential flat earther, and potentially you think that gravity isn't a thing, hopefully this is getting you somewhere. All right? And you don't have to be an idiot and put your name on something so ridiculous as this chapter. All right, so, okay, that's it for this one. If you can just unshare, please. How are we going for time in your
I'm fine.
Okay, good.
I have not yet run out of coffee, so
okay.
I can keep rocking.
Okay, so if you can just unshare that for me, please, then I can we can keep moving on. There's a couple more things that we have to get through, and then we'll do our scoring. I think we're ready to do the scoring now, so.
There we go. All right.
Okay, all right, so let me close that one down.
All right. While you're doing that, let me I'll get a little more.
Yeah, you go through that, and I'm also going to get myself a drink, so I'm going to go for a minute, okay?
All right. Sounds good.
All right, so you answer those, you read those things, and I'll be gone for just a few minutes.
All right, sounds good. All right. Now, Basil Problem, he wants a wrench. And I'm like, Basil Problem, bribery. You're going to have to bribe me a little harder. So, and I gave him my Cash App. It's hard. It's really hard. MCToon. You'd never know. My Cash App is just MCToon. So just, if you want that wrench, I don't know, start big. I'll just say that, Basil Problem. Start big if you're looking for that wrench. And you might say, but that's extortion. Yes, it is. Okay, Icy Spin says, how does a helicopter fly with 1,000 miles per hour to the wind? Checkmate. I already read that. All right. This is Basil Problem's second super chat. And so it is at the $5 tier. And so this shall be read. Says MC2, next stream idea, dimensional analysis. Let's convert pressure to moles. And I suppose you can't directly convert pressure to moles, but you can use moles in your final answer, I suppose, as one of the units. If you start with pressure, that I don't know how that would be very exciting, but you know what, Basil Problem? Maybe you could do that on your channel. I'll definitely not watch that. The Drunk Debunk Show for $10 says we can't measure it because we don't have a ruler long enough. We had the disgraced low end grunt surveyor, the guy that holds the stick, Raymond. He was in here for a little bit, and he was derping about the hump in the water at the equator, and claiming that somehow it doesn't exist. But of course it does. It's been measured. mctoon.net/r has a list of measurements, really good and high-end measurement surveys, in fact, of the dimensions of the Earth. showing that it is in fact has a larger radius at the equator than at the poles. So suck that, Raymond. Inquisitive Infidel says Flerfs define nature according to whether they like the result of the experiment. If they can spin the presumptions, then they'll claim it's indisputable. That is absolutely their MO. This whole thing that's in this book that QE invented these definitions of science is just so that they can ignore any science that they don't like. They take this. It's just this smorgasbord, as Phil mentioned earlier, used that word earlier, of things in this list of what science must be. And then they take any experiment that you bring to them and like, oh, nope, it didn't match this, it didn't match this, it didn't match this, right? They just go down all these things claiming what it doesn't match. But, right, none of it is correct. None of it is how science is actually done. Scientists do not use that criteria when examining other scientists' work. It's never happened in the annals of science has another scientist said, well, what's the IV and the DV? No, they just go read it. And then they use their brain to see if it makes sense. And if it doesn't, then they'll write a review of it, and they will publish that as a response to the previous one in a journal, maybe the same journal, maybe in a different journal. That's how science is done, not just basically saying, what's the IV and DV? And you didn't do this, and you don't. That was a man-made apparatus, therefore it's not allowed. Seriously, nobody in the history of science has ever rejected any experiment because it used a man-made apparatus. But the irony is, of course, then they go and they cite whatever they want to cite that they think supports them, that they should reject because it doesn't match all of the invented garbage things about science that they think they should be using. Of course, it's just all BS. All BS. And now I've got this final one here from IC Spin coming up. All right. Are you back? Can you hear?
Yeah, I can. Yep, I'm back now. So
IC Spin says, Professor Phil Bell, your color scheme is 1,000% greater than Quantum Eraser's color scheme.
There you go. Okay. All right. Shall we carry on? Let's see if we can get the audience now to go over the rubric. Get your scores together. Okay.
All right.
All right. And then we can quantify them and maybe announce them later if we have to do some statistical analysis of them. Although we can probably look at the data pretty quickly and have a look. All right. So let me just open that up. Okay, so number 4. Okay, the rubric scores. Okay. All right, so
are you sharing it?
Not yet. I will get
right.
there. Start it first. Watch from the beginning. Okay, and then sharing. Yeah.
Oh, I'm just like leafing through the book. He's got a picture he's got this triangle, right? It's hard to see. Hold on. Let's see if we can get a better. He's got this triangle right here. Look at this. Right? Of celestial navigation. So he's claiming that the star is a very specific physical elevation above the surface of flat Earth. How far is that? Well, if you know your distance across here and you know these angles, then that star must physically be a certain elevation above flat Earth. This is testable. We can go somewhere else and do the same construct the same triangle to see if it matches and to see if the star is the same elevation in different locations. When we do that, it's not. Every single time it fails. And what does that mean? That means flat Earth is falsified.
Absolutely.
But
So this is one of the things. Yeah. So one of the things Oakley does, and he says, well, it's the circles of equal elevation. He calls that. So they're concentric circles around the North Pole, and they are. And we know that there's 60 nautical miles for every degree, or 69.1 miles for every degree. Well, they aren't if it's flat. They can't be if it's flat. Okay.
Yeah, the geometry. You add a second location, it doesn't work anymore.
Doesn't work. And the other thing about it is, well, if that's true, then, and let's just say that you got that. Well, at zero, what happens after zero? Why is it zero? Why didn't you just make it 100? Why didn't you just make the next 10 110 and 120, 130 and all that? Why zero? All right. Well, maybe because you couldn't see it. So does that mean that? So now you've got to use some other means to work out. What was the other means that you used to work out the rest of it? None of that seems. That doesn't even occur to.
Can I? I want to show something here.
Yeah. Yeah. You stop the sharing if you want. I can just.
No, I'm sharing. So here's a book, Zetetic Cosmogony, by Thomas Winship. This is an older book reprinted. Here's that triangle that Quantum Eraser just put up there. These are in the book here. He's talking about here locations on the surface of the Earth, 45 degrees north latitude. And he's concluding, quote, the sun is therefore 2,700 miles, nautical miles, he's saying, distant from the Earth. This flat earther is making that very specific claim by only measuring a single triangle. That's it. One single triangle is all that he measured. And flat earthers today know that you don't do that. You don't dare do that because other people can go measure other triangles.
Yeah, exactly. Yeah, exactly. All right. Okay, so here we go. All right, let's go back to this. So all right, so the science writing and language critique. Okay. Let me see if this is the Rubik one. Okay, so all right, so here we go. Remember, if just to refresh your memory, okay, of what you are marking. So use of scientific technology. So you had a choice of 0, 1, 3, or 5. So it's out of 5, and so on. Structure and logic, the use of evidence, tone and objectivity, argumentation quality, and then literature maturity. So all out of 5. So the whole thing's out of 30. So you're going to mark things out of 30. Okay. All right. Okay. So here, this is my view of it. All right. So don't be swayed by what I agree, what I think. I'll make my case. You can make yours. Okay. So use of scientific terminology. Okay. I'm giving it a 1 out of 5. That's low. Terms are used rhetorically or incorrectly. Okay. All right. From the chapter, non sequitur, category error, reification fallacy examples. Density is not a natural phenomenon. Okay. So I think they don't know that density is a calculated value from mass and volume. And big G is bastardization. All right. So conclusion: the chapter reaches constantly for technical and logical fallacy vocabulary, but applies it incorrectly, branding a measurement density not a natural phenomenon. I mean that is just stupid at its finest. Okay, or general relativity, a reification fallacy. A handful of terms are at least defined. Pseudoscience law is law versus theory, which keeps it off the floor, but the definitions are bent to fit the conclusion. So why aren't I giving it a higher score than this? Excuse me, I just got that alarm. Okay. How do you switch this thing off? I'll just hit snooze. We'll probably come back again then. Okay. Okay, I'll do that in a bit. All right. Okay. So branding a measured density, not an actual phenomenon or general relativity. Okay. It's a handful of terms are at least defined. I read that. Okay. So why not higher? Well, some terms are defined, so it's clear. So clear is very, very low. So we're not going to give it 0, but they work as weapons, not tools. Right. So I'm giving it a 1 for that one. Okay, for 2, okay, structure and logical progression, I'm giving it a 1 out of 5 again. So frequent digressions, unclear progression, or circular reasoning. The evidence from the chapter, a necessary detour, the author's own words. Okay, Cavendish presupposes a debunked force. There you go, the digression. The linguistic puppeteers that flourish. Okay, excursion on maths. Okay, so the argument, so the conclusion of the argument repeatedly leaves its track. Most strikingly is a multi-range laws of physics / maths isn't science. Okay, excursion, the author himself concedes it is a detour. So he actually tells you how to think. So this author, one of the biggest things that they tell you that ordinary people are brainwashed, and in this very chapter, this author tells you how to think. Okay, all right. So
the irony.
Okay. The irony. Yeah. Okay. All right. So it also reasons in a circle, dismissing the Cavendish result because it presupposes the very thing that's in dispute. Okay. A through line exists, but it keeps wandering and doubling back. So, all right. So a discernible spine keeps it above very low. All right. Yeah, so only just. Okay, and the diagnosis and circularly keep it at low. So I think I'm being generous, but
You
there
are.
go. So I'm going to give it a low. I think very generous here. Okay, use of evidence. I've given that a flat out 0, very low. Okay, evidence is misrepresented or absent. So if there is any evidence over there, it's completely misrepresented or it's completely absent. And let's get a look at some evidence from that. Newton's 1692 letter, recast as renouncing gravity. We've spoken about that before, right? Total misrepresentation of what Newton said. Not a force, quoted to mean not real, okay? And quote stacks that manufacture authority. So not a force, not real. So that's used to discount gravity. So it's not a force, can't be gravity. And then, for instance, the other thing is that, of course, if we say gravity is the reason that we have the pressure gradient, well, it's not a force, so how can it be? Again, declare it to be not a force so that you can dismiss all the other things. Declare space to be fake so that you can completely dismiss actual photos of the Earth from space. That's the way that they do it. So in conclusion, sources are not merely underanalyzed; they are actively misrepresented. That's true, and I believe they know that they're misrepresented. So they're not. They by now, this isn't an accident. It's not a mistake. They actually know it. Okay, so Newton's unease about a mechanism becomes Newton's renounces gravity, total misrepresentation. Physicists, gravity is not a Newtonian force, becomes gravity is fiction. So you see how they use something and then completely change it. So that they say gravity is fiction because somebody's saying gravity is not a force. Okay, so quotation is so imagine all the damage that Brian Cox has given to that. By saying that he hasn't really, but for the flat Earth community. Okay, so quotation is abundant, plenty of them, right? But it functions as a wall of authority rather than analyzed evidence. And none of those quotations are actually evidence of anything. They just use there just to try and give a misrepresentation some sort of credibility that it doesn't deserve. So misrepresentation is the chapter's engine. Okay, the rubric's definition of very low. So that's why I've given it very low. I think well deserved. Okay, the next one, which is number 4, the tone and objectivity. What objectivity is my question. Okay, the tone is sarcastic, it's ridiculing or polemical. And so from the chapter, por favor, seriously, you put your name to this. Okay, a final thumb in the eye for Einstein. Another bit of flourish. Just say it, and it'll be true. It'll come true. NASA hasn't kept up for 111 years. Really? But they just use all of Newton's stuff. They use all of Newton's laws in order to do all the things that NASA does, and they haven't kept up. Seriously? Did that even cross any one of those minds, of those two authors that did this? Parlor trick. Another one of those. Another thing. If I say the word that it's a parlor trick, that'll give a phrase, yeah, for those people who want to discount it, not for any good reason. Just call it a parlor trick, and then it will be. Okay, cosmetic slapstick. Another phrase that they use. Right. So the register is openly mocking. Okay, and polemical, and from the first page to the last, ridicule of NASA, of Einstein, of every opponent. In fact, there's essentially no neutral analytical voice anywhere to affect it. Okay, this is the rubric. This is why this rubric's a very low descriptor, almost word for word from that. So if you read the rubric, read this, that it's word for word what it is in the very low. So sarcasm here is not reasoning. It's not seasoning.
This one is so low. It's unfair to give it a 0.
I think it needs to be minus.
Yeah.
It is the main ingredient. Unambiguously very low. You can't get it. You couldn't be more. This could not fit the rubric more closely than. They couldn't have done a better job fitting this to a rubric. Okay. All right. Let's keep going. All right. The argumentation quality. All right. So again, this is very low. Didn't exist. Argument relies on rhetoric, emotion, or mischaracterization. That happens all the time. There's actually nothing, not a single thing that you could say is doesn't fit that criteria. Not a thing in this chapter. Okay. So from the chapter, just examples: model and model not equal to phenomenon. Okay, the two swapped throughout, so they're using the word model, and so typical things that they'll say, we don't live on a model. Then you don't know what a model is if you're saying something like that. Okay. Can you bend freedom? Again. That's painful. And then death blow. Really? So all the satellites, all these space rockets that are going up every second day, they're just all going to stop. It's all for nothing. Really? Okay, the death blow. Non sequitur from the Black Lagoon. That again, that flourish, this meaningless flourish. What is the relationship between that non sequitur and the Black Lagoon? I don't know. Were they talking about black holes? I don't think so. Not even that. It didn't even get cut that close. All right. The central move is mischaracterization. That's completely all of it. All that it is, treating a change of model, Newton to Einstein, as proof that the phenomenon is fake. Right? Why? Okay. Even if you discounted Newton's, which was just done because that's what's used mostly, and you discounted that, then why is Einstein's fake? For that, just because one is fake means the other is. Okay. Although it reoccurs every section. There's no place where they don't do this kind of mischaracterization, where reasoning should appear. Okay, loaded rhetorical questions and theatrical phrases stand in its place. So that's for them, for these two authors anyway. If you have a nice flourish, some mischaracterization, some clever rhetoric, then that automatically is enough to discount the evidence that's obvious there. So, so why didn't I go higher than zero? Well, reliance on rhetoric and mischaracterization is exactly what defines very low. All right, nearly there. Okay, what number is this? This is 5 or 6. Okay. All right, literary maturity. So this is the last one. Okay, so is this a mature piece of writing? You know, is this something that an adult would want to read or should read? Okay. All right. So I gave it a 1. I thought I'd be generous. Okay. Right. Low writing is, I'll tell you why I gave it a 1, because it has got some flourish in it. And if you wanted to read it as some sort of slapstick, then as they put it, then it probably works for that. Writing is repetitive, digressive, or emotionally driven. The finale dips towards very low. It's theatrical and rhetorical, so it is pretty generous, giving it a low instead of a very low. Okay, grand theater, invisible prima donna, cosmic slapstick. These are words used in this text. This is a scientific text that has words like grand theater, invisible, prima donna, cosmic. They're in the science, really. None of these people could have ever properly read any science text. Otherwise, they would not use words like these in science and then expect to be taken seriously. Yet no one ever bothered to audition anyone else. There you go. All right. Conclusion. Right. It's emotionally driven and digressive, and the whatever I will in there. That's right. Peroration tips into the rubrics very low. Okay, theatrical diminished by flourish. So what risk is it is to low. So in other words, what takes it from very low to low is genuine ability. This ability to add flourish. Okay, it controls this. Although they can add flourish, it's completely disjointed and has no you know, it's undisciplined. Okay, is the way I'd put it. Okay. So why isn't it higher? Real writerly instinct tips it to low. Discipline. That's what that needs. Discipline would be needed for anything more. So yeah. So there's some flourish there. And if this was aimed in a different way, it wasn't aimed as a scientific writing, then you know, if it was a bunch of comedy or slapstick or something like that, then there's some clever flourish there. So, but it's not. It's meant to be science. That's why we're marking it.
Yeah,
Okay.
they definitely do try to present it as science.
Yes, they do. Yeah, and it's definitely less than.
I think the this is a story part at the beginning was done. This is a work of fiction, that he said at the beginning. If I understand right, it was done because they thought that you can't copyright science or facts or something like that. And so they're like, oh, let's make it fiction. And then they added in this fictional character that's actually a real person. But fictional character that both Quantum Eraser or John Stunja and Adam like wrote in. And I imagine that it was John, because this character is just fawning over John. Just can't get enough of him. She is just enraptured with how amazing he is. This is John fantasizing through her about him. It's very disturbing.
Well, just on that stupidity alone, on that, I've got a shelf full of mathematics books and physics and stuff like that around the place, and each and every one of them is protected by copyright.
Yes,
and yet they all say the same thing.
Yes.
Okay. All right. So why do they get 3 out of 30, which is 10%? Okay. Well, okay. The two analyses agree. Right. Free-form critique and the formal rubric land in the same place. energetic prose, immature execution, no scientific discipline whatsoever. Okay, it fails the hardest when it matters most. Okay, in three zones. Evidence, tone, argumentation are the core of scientific writing. This is not an accident of style. It is the method. Okay, the ones are not flattery. Okay, right. Terminology, structure, and literary maturity scrape a point each because the chapter defines a few terms, keeps a loose spine, and shows real voice. Okay, maturity is missing variable. Every strength, every strength it has is rhetorical. Every weakness is disciplinary. The gap between them is exactly maturity. There is none. Okay, it's low, right? A capable but immature writer is here. Yes, they clever at the flourish, but it's not working in a genre, in this genre, which is science. Okay, and to a standard that the writing has not yet learned to meet. So they are in the wrong place. Okay, they don't have what it takes to be here arguing anything about science at all. Okay. All right. So that's it. So let's look at the scores. 1-1, 3 1s. That gave him 3 out of 30 for all of that, and that's the end of their that's my take on it. It'll be interesting to see what the audience say. If you don't mind, you can talk through a few super chats if you have any, and then I'll prepare for the last bit.
I for me, I didn't write down, but I tend to agree. It's easy to just say zeros across the board, but yeah. I think you're fair in giving a couple points here and there for some of the things that you did give. But like I said, the tone and objectivity, I think is being generous, giving it a 0. It is not just a 0 in tone. It truly is purely the tone is purely just negative. It's all negative. Yeah, that is Quantum Eraser's MO. It always has been. It's just insulty all the time. He works up to when he's going to present something with insults. He presents his thing, which isn't a thing, and then he finishes after that with more insults. So for me, I would give the tone a -5. And I think the other ones I would agree with, and then give him, take it from a +5 to a -2 out of 30.
Okay. All right. Well, I haven't got a slide for my last bit, so I'm just going to go through my conclusion.
Okay.
That's just my final conclusion about the whole thing, and then we can see what we get from the audience. Okay. So this is my final. So the writer of this chapter is immature, but not completely untalented. Right. To be fair. Right. And that needs saying as plainly as the criticism did. Okay, so what follows, however, is not that the work of someone nurturing, developing skills, but this is of someone who's overestimating it. Right? It's a sequence of trained choices, uneven execution. Strained choices, not trained, strained choices, uneven execution, and confident misjudgments and misrepresentations that reveal how far the writing sits from genuine competence. So they couldn't be further apart. So the gestures towards techniques feel more like attempts to imitate what good science writing looks like, rather than evidence of understanding how it actually works. So every one of these gestures runs without a break. The voice slides into mockery, the images pile up faster than they land, and emphasis is shouted rather than named. The result swings between genuinely well-made sentences and overcooked ones. And that very unevenness is the tell. It marks emerging ability, which they have, that hasn't yet met discipline. That said, two things keep this judgment honest. First, none of it speaks to whether the arguments themselves is sound. It's not. Right. A person can win with flair in service of a badly mistaken case. And that's exactly what's happening here. Writing craft and correctness are separate verdicts. Second, what's being salvaged from this wreckage is rhetorical and literary instinct, not quite the different skill of disciplined expository science writing, which of course the chapter gives little evidence of, and which the subject demanded. So in the end, it reads not as emerging competence, but as enthusiasm masquerading as expertise, delivered with the misplaced certainty of someone convinced that they're contributing to scientific literature. So here's the fairest summary. We're looking at capable, albeit thoroughly immature writing, offering this inadequate at their best. So they're working at their best, but it's immature. Right? A piece straining against the genre and standard well beyond the reach of someone with their sparse intellect, talking about both of them. And honestly, the real waste isn't the writing itself. It's the time spent humoring baseless arguments, that all of which collapse under the slightest scrutiny. And not because they lack ability entirely, but because whatever ability they do have is left inadequate, undisciplined, untrained, yet somehow convinces themselves it passes for scientific literature. Thank you.
Well, very good.
All right, it's up to the audience now.
Yeah, if you have comments or questions, if you tag Conspiracy Tunes, it'll show up right here, highlighted, and my scraper will get it so I can put it on screen if there's a few that want to comment. In the meantime, Real Jiffy Cone says, terrible pickup line, hey baby, want to explore my South Pole together? I've never seen it myself. Slithery has a member super chat that says bleep. And then Icy Spin says later, gents, thanks Phil, always a pleasure. So I think Icy Spin unfortunately has work tomorrow. Always getting in the way of fun. So
yes, it does. It has a way of doing that.
All right. Hugh Jars says, Professor Phil, why are you so awesome?
Oh, there you go. Okay. Speak for yourself, Hugh Jars. He's the one who's awesome.
Let's see. Basil Problem said, next stream, let's compute the Taylor series of e to the power of x. Will it converge? Let's not spoil it. I you know what? I gave him that. He didn't even pay the requisite $10 extortion fee. I was too generous.
Well, I didn't pay for this, by the way, because there are flat earthers in the Oakley team who are quite happy to hand out other people's works for free.
Yeah, the PDF was obtained by a flat earther and distributed by a flat earther when shortly after this book came out. And Oakley, a fan of Oakley, who doesn't like QE because there's a schism in the.
Yes, so there you go.
Basil Problem, you know what? Because he's actually being a decent human right now. He says, Professor Phil Bell, great presentation. I enjoyed it. Twice I read non-extorted messages from him. Man, I'm getting soft. All right. So you said you also have a treatment on his claimed second law of thermodynamics.
Yes. So if you'd like to
Violation.
do that, I'll be happy to do the thermodynamics.
Yeah, certainly not tonight. But
Not
yeah,
tonight.
maybe.
I'm thoroughly exhausted after that.
Let's see here. Mr. E-Man says, I did not get an answer to why I cannot mark this work as, that's why, because this, you see the super chat here, not the super chat, the comment did not pick up the emojis. Probably a bug in my code. And I didn't see the comment. I just saw the scraped comment and I read it. But now I see you, like, it's right here on the screen, right? If you look over here, people right there, that's his comment. So why can't I mark it as, and then a whole bunch of chocolate ice cream emojis.
Okay.
So let's see.
You
Max,
follow the rubric.
Yes. Max says, thank you, Phil. Thorough debunking right there. Huge R says, not as soft as me. All right, there you go. Well, I think that's that. So, if I hope you don't mind, I took the PDFs that you sent me. I uploaded them to the Flerf wiki.
Oh, excellent! Thank you. That's good.
And so people, and I put the link in there, but the Flerf wiki is currently getting a 503, so it could be too much traffic because I only pay for a certain amount of server, CPU, and it may be over that right now. So I will, if it continues, then I will have to put in a ticket. But my guess is that I probably need to increase how much I pay them. So
if anybody wants to do the homework, don't forget that homework's there. Okay, if anybody wants to do the homework, then by all means just send me an email and or a message on Discord, whatever, and I will send you the homework. Okay, which we can discuss. Now, I love to do the thermodynamics. I love to do why space is not fake. Okay, all right, that's a must do, and then there's a couple of other chapters that are interesting, but especially that one. I'd like to do that.
Okay.
Well,
let me see here. There is a song somebody wrote for QE. There it is. I've got it queued up. So anyway, people, and Phil Bell, thank you for joining. Anything else before we head out?
Okay, so one last thing. If you got your scores, then put your scores down together and let's talk about let's try and see. We can just quickly write down how much out of 30, and then we can work out if anybody has got anything more than 3. That will be great. Be interesting. Okay.
Yeah, put it in the chat quick if you let's see. We got Aldebrand has negative 32. May not have applied the rubric quite how you did. My guess is that people mostly were just following along and not actually writing things down.
No, I guess
Big Fish gave it a 2 out of 30.
Yeah. Okay.
Huge Arse.
Not going to be an outlier.
Huge Arse gave it minus a Googleplex.
Oh, okay. All right. That's going to be an outlier.
Yep. Real Cygnus says 3. So, yeah, of those that
range.
Yeah, I think
that responded. So I think 2 or 3 is about where it should be sitting.
Yeah.
Yeah. Okay. That is embarrassing. These people should be ashamed of themselves putting their names to stuff like this.
PG Tony gave it a 2 out of 32. I don't know how he gets 32 out of the rubric. X Forbidden One gave it 42 out of 30. PhD Tony corrected himself, 2 out of 30, not 32. There we go.
All right. Anything from Clive? Is still there?
Clive, or as Mallory says, Sleeve Wells.
Yeah.
He may. I think it might be a little late for him.
Okay. Yeah.
He's
probably,
in. I think he's in England land, if I'm not mistaken.
Yeah. Yes, it'll be pretty late for them. Yeah. Okay. All right. Well, that's it. That was real fun. Exhausting, but fun. Okay. So yeah, thanks very much, Michael, for doing that. I really wanted to hoe into that particular thing and do it without too much mocking.
Yeah, and that was a serious treatment of it, and
yes, I think
maybe more serious than it deserves, but I appreciate that. So tomorrow, I probably will be doing a live stream. We'll see. I'm not 100% certain. Next week, I'm out of town. I will be doing something while out of town, including some globe activism. That's on the plan. Okay. And so anyway, everybody, thank you very much, and we'll see you next time.
Yeah. Okay. Au revoir. Sing along. He stares at the planet from behind the locked door, calls his audience the army, and his ego is the war. He won't take a debate that he didn't get to call. He won't show on the screen where he doesn't run it all. But the moment that a critic puts a book review online, he's not a debater anymore. He's a clerk on the line. He fires up his email. He files every form. The Louisville Slugger is a takedown swarm. Couldn't lock the Facebook. Take the heat, couldn't take a book review without a takedown sheet. Filed a copyright strike, filed a privacy claim. The bravest little Flerf, hiding from his name. Couldn't lock the Facebook. Couldn't lock the Facebook. Couldn't lock the Facebook. Couldn't lock the door, but he'll lock down a critic with the copyright war. Couldn't toggle friends only on his profile wall. Wrote a whole book that he says explains it all. Couldn't lock the Facebook. Couldn't lock the Facebook. He read one freshman handout, called it the only way. Now he chants the scientific method every single day. He decided astronomy and cosmology are trash. Geology, paleontology, a 4 billion year flash. He says gas needs a container or the globe can't hold air. He says Einstein had no hypothesis worth a care. He says Newton renounced gravity, but he stops in the middle. The very next line would have solved the riddle. He explains it to his cult while they nod and they bow. Every misread is a sermon, every misquote a vow. And when the world says John just read what you skipped, he fires up the tape down till the channel gets clipped. Couldn't lock the Facebook. Couldn't take the heat. Couldn't take a book review without a takedown sheet. Filed a copyright strike. Filed a privacy claim. The bravest little
2013, MCToon reviewed his book online, critical mocking fair use, every clip within the line. April 16, book review 2 went up the same way, with photos that John posted to a public profile display. A few hours later, the takedown emails flew, copyright strike for a critique on his fair use review, plus 3 privacy strikes on a face he made known. On the same Facebook page he had publicly grown, he's got a Louisville slugger with the nails in the wood, but he won't leave his server like a real prophet would. He talks about the woodshed, talks about the firing squad, but the threats are all hot air from a digital god. The cult is the cage and the cage is the cult, and the prophet loves the bars cause he knows he's the result. Numpty ball Todd, Mr. Magoo on the wall, but the bravest little Flerf can't stand up to a call. Won't debate on a stream, won't argue without pay, won't show up on a podcast, won't show up on the day, but he'll click submit on a YouTube takedown form. The bravest little Flerf